Hello, and in this video we are continuing our work with collisions in 2D, and really we're just going to extend what we looked at last time, and now we're going to consider bounces off multiple walls and surfaces, right? So we're not really going to do anything new here, and again to remind you, this is year 2 content, so the full A level. If you're doing AS, you don't need to worry about this, okay? It's just for the full A level. But I thought I'd remind you there, okay? Now, actually, before we start, just for those who are quite visual, I just want to show these fun little visuals to represent what's happening here very quickly. Okay, so this is the first visual. So you can see the ball is bouncing multiple times, right from the ground to the wall and vice versa, right? And so that's what we're going to be looking at, basically bouncing off multiple things, right? I'd also thought I'd show this fun little visual. So you might be familiar with this, the DVD logo, which annoyingly never perfectly reaches the corner, right? But again, it's kind of the what's going on here is kind of what we're going to be looking at as well. Again, you can see it's bouncing off multiple walls, right? And it's just going all over the place, right? At different angles and stuff like that. So we're going to be exploring that sort of motion, okay? But I thought that'd be a bit fun to show. Okay, so we've got this question here first. So here we're told 2 walls stand on the floor and intersect at right angles. The walls and the floor are modelled as smooth. A smooth sphere is moving across the surface and bounces off each wall in turn. At the moment, just before the first impact, the sphere speed 2 at an angle 30 to the wall. Coefficient restitution between the sphere and the walls is 0.5, and so we need to find the speed and direction of motion after the first and second collision. Okay, so what's going on here is, so this is the trajectory or the movement of the particle. So the particle moves like this to the first wall, right? Then it bounces up to the second wall here, and then it bounces off that, okay? So you can see we've got 2 collisions, right? A collision with each wall. And you can also note that the walls are at right angles here, okay? So one's horizontal, one's vertical there, okay? But pretty much all the information we are given on the diagram, okay? So what's the process here? Well, we're going to do the same thing that we saw last time, but because there's 2 collisions, it's a good idea to consider them separately, right? So this is my first collision, and I'm just going to draw out what the first collision only will look like. So it's going to bounce off the floor, right? This horizontal floor here, and so it approaches the floor, as you can see here, with speed 2 and an angle 30. Then it's going to rebound with some speed v and an angle, let's say beta, okay? So and so at that point, again, we're going to do the same procedure. Now we're going to split things up parallel perpendicular. So firstly, this speed here is going to go down here, then across the floor. Then afterwards, it's going to go across the floor, then back up like this. Hopefully happy with the resolving there. Okay, so hopefully you are comfortable with that by now, but there we are. Okay, then I can label what the components are. So this is going to be 2 sine 30 here. Again, it's sine because it's opposite the angle, okay, and this is then going to be 2 cos 30 because it's adjacent or next to the angle, okay. Likewise, this bit's going to be v cos beta here and v sine beta there. Now I'm going to consider my parallel and perpendicular parts, right, as usual, right. So the parallel parts, well, that's going to be along the floor, remember. So that's going to be this part v cos beta is going to equal the parallel part before, which is 2 cos 30, right? Because remember the parallel speeds are equal, okay? Actually, we can simplify this because we can work out 2 cos 30, right? So that's going to be v cos beta. So work that out quickly. we get root 3. Okay, make sure your calculator is in degrees mode here, not radians. For mechanics, we tend to use degrees, which is very confusing because pure you usually use radians, right? So don't make silly mistakes by making sure it's in the right mode. Okay, but there we are. So you should get this equation here. Then perpendicular. So the perpendicular components, well, v sine beta, that's the perpendicular at right angle to the floor. Well, that's going to be 2 sine 30, but it's going to be e lots of it, right? Because the coefficient restitution acts perpendicular. Okay. And there we are. And actually, we can simplify this because firstly, we know that E, the coefficient restitution, is 0.5. So it's going to be 0.5 lots of 2 sine 30. Then we can work all that out to simply get, if we work this out, that V sine beta is a half. Okay. And there we are. That's my second equation here. Okay, so if I label these equations 1 and 2, okay, so firstly then, so we want to work out the speed v and the angle beta. Now remember, the common techniques are we want to square the equations to work out the speed. So firstly, if I square them then add them, right, so that's going to be v squared cos squared beta add v squared sine squared beta. It's going to be root 3 squared add a half squared. Hopefully you're happy with that, right? So I'm just squaring both equations and adding them. Okay. Then I can factor a v squared out, and hopefully you can see what will happen here. Okay. And then if we simplify the right hand side, so root 3 squared will be 3 and a half squared will be a quarter. So 3 and a quarter is 13 over 3. And hopefully you realise that this is equal to 1. Again, very standard procedure. We've seen this last time. So therefore we just get v squared to be 13 over 4. And quite nicely then we get v, if we square root this, to get root 13 over 2. And there's my answer for the speed v there. Okay. Right, then I want to find the angle beta. Okay, so to do that, instead of squaring them, I'm going to divide them, right? Because hopefully you realise I can get tan. Okay, so specifically I'm going to do the second one divided by the first one, because as I mentioned, I'm going to get tan. So if I do v sine beta over v cos beta, that's going to be a half divided by root 3. So hopefully you can see that, right? I'm dividing the second equation by the first one, which will get me v sine beta over v cos beta is a half divided by root 3. Hopefully happy with that. So I can simplify this now. Now the v's cancel. Okay. So we just get we just have beta. So that means tan beta, because again sine over cos is tan. So tan beta, if I simplify this fraction here, so if I do a half divided by root 3, I get root 3 over 6. And so there we are. Therefore, I can get beta by doing inverse tan of this. And so if I'll do that, I get my angle to be 16.1 degrees to 1 decimal place there. Okay, so there we are. Now the question was asking for the speed and direction of motion. Now direction of motion basically is the angle. Okay, so the angle here, again, if you look at my diagram, that would be beta, right? Hopefully you can see that right on the diagram here. So that's the trajectory, that's the angle I'm moving at. So that's basically my direction of motion. So direction of motion literally just means the angle. Okay, so we've worked that out. Then we need to do the same for the second collision. Now, at the second collision, obviously it's gonna then move like this and hit the vertical wall like that. Okay, so we need to consider this part now. Okay, so let's draw that out. Okay. So now let's do the second collision. So now we've got the vertical wall, right? So now we're hitting the vertical wall, so it's going to look like that, all right? So this is my speed v, but we know that v is root 13 over 2. So root 13 over 2 is the speed it approaches the second wall. And then it's going to have some speed afterwards. I'm going to call w. Okay. Hopefully happy with that. Now, in terms of angles, this angle first. Now, you might think just call it a different angle. But actually, we can work out what this angle is going to be as it approaches the second wall. Because, if I look at my diagram, this is beta, right? And actually, if I zoom in on this triangle we've got here, then, right? So if I recreate that triangle, and this is the main idea with these problems, is that if I know this angle's beta, so beta here, again, hopefully you're with me here, which we worked out previously. Well, actually, right angle triangle, we can work out this angle here. And so that's, hopefully you can see, has to be 90 take away beta, because if all the angles have to add up to 180 in a triangle, 180 take away 90 here, take away beta, leaves me with 90 take away beta for this remaining angle there. So this is 90 take away beta. Okay, so that's the angle. Hopefully you can appreciate is going to be this angle here, 90 take away beta. Okay. And then I'm going to call this a different angle theta after it rebounds off this wall here. Okay, now, okay. So if I was to now do the components, so it's going to go across like this and up the wall, then up the wall here, then across like this. Now you might be tempted. Now you might say, well, if I was to look at my resolving the normal in the normal way, right? So this would be root 13 over 2 sine of 90 take away beta, and then this would be root 13 over 2 cos of 90 take away beta, right? Okay, so hopefully happy with that resolving then, right? And so again, sine is opposite or facing the angle, and then cos is adjacent to it. So it's all perfectly correct, right? Hopefully happy with that. But you might be thinking, well, we've got an awkward angle here. We've not got a simple, straightforward angle. We've got 90 take away beta, right? But then you might be thinking, well, I've worked out that beta is 16.1, roughly, right? So I can sub that in to get the angle, right? And then go from there. But we probably shouldn't do that for two reasons, really. One, obviously it will produce an awkward decimal, right? So we won't get an exact answer. So we kind of want to avoid using decimals too early if we can, and avoiding rounding and stuff like that. But actually notice that actually this angle here is beta, right? So if I get rid of this now, okay, so again, if I was to extend the floor that we looked at before, right, that's just the angle beta, isn't it, right? Again, that will be 90 degrees. Well, actually, can't we just go back to SOHCAHTOA and then say that alternatively, our components are, if I just consider the angle beta here, this is going to be cos. So here it's going to be root 13 over 2 cos beta, and then root 13 over 2 sine beta. Okay, hopefully happy with that, right? Because now beta's here, so this part will be cos and this part will be sine. Okay, and that's a lot nicer, right? It's just a straightforward angle beta, so I don't have to sub my numbers in prematurely, right? And it works out quite nicely. Okay, so that's the strategy, right? Especially when it's 90 degrees, it works out quite nicely like this. So so there we are. Okay, so there we are. So hopefully happy with that, right? So I don't have to do 90 take away beta. I can just consider the angle beta here instead. Okay, and then resolve that way. Okay, then as for up here, then, well, this is going to be W cos theta and then W sine theta here. Okay, and there we are, right? So now, again, if I now look at my components, well, my parallel components, firstly, now this is going to be parallel to the wall here, the vertical wall. So the parts that are parallel or along the wall, well, it's going to be this part and this part here. So W cos theta is going to equal root 13 over 2 sine beta. Okay. And likewise for the perpendicular component. Well, the perpendicular component that's perpendicular to the wall, well, it's going to be the W sine theta here and the root 13 over 2 cos beta there. So W sine theta is going to be, remember, E lots of the root 13 over 2 cos. Okay, so hopefully happy with that. Hopefully happy with the parallel and the perpendicular components here. Okay, now in terms of simplification, because we just have sine beta here, if I have a look and if I revisit my working, I know what tan beta is. So that actually gives me a way to work out sine and cos, right? Because if I now do a triangle here, right? And I'm going to call it beta, and hopefully you're going to be aware of the technique I'm going to do, because hopefully you would have seen this before in previous chapters. The idea is, if this is tan, again, if I think back to Successive, the root 3 has to be the opposite, and the 6 has to be the adjacent, right? Because tan's opposite over adjacent, right? I'll make it clear here. So it's the opposite over adjacent. So the opposite side is going to be root 3 here and 6 there for the adjacent. So if I now work out the hypotenuse of this triangle here, I've got, let me get rid of this now actually. Okay, so hopefully happy with that, right? So I'm just considering the sort of the triangle we can make here from the tan of the angle using Successive. Okay, now if I work out the hypotenuse, Pythagoras, right? So root 3 squared over plus 6 squared, that's going to be 39. So it's going to be root 39 for the hypotenuse there. Therefore, we can work out sine and cos of beta. Okay, and that's going to help me with to simplify my equations that I've got waiting for me. So sine beta, well, that's going to be due to Successive, opposite of a hypotenuse, so root 3 over root 39. And then I can do the same for cos. So cos beta, well, that's going to be adjacent over hypotenuse, so 6 over root 39. And there we are. Okay. So I've got expressions for sine and cos, so I can sub those in my equations here. Okay, so hopefully with me there, right? So so sine beta, again, so that's going to be root 13 over 2, lots of sine of beta, which we just worked out to be root 3 over root 39. Okay. And so that will get me that W cos theta. If I work out root 13 over 2 times by root 3 over root 39 to be a half. Okay, which is quite nice, right? Now, imagine if we didn't, imagine if we just subbed in the angle beta as a decimal rounded, we would not get half exactly. So that's another reason why it's important to try and not use decimals and round earlier than we need to, right? Because we might be missing out on exact answers. like that. Okay, so there we are. Likewise then, sine W sine theta. Well, firstly E, remember E's a half, right? And then we're going to times by root 13 over 2, lots of cos beta. Now cos beta is 6 over root 39. 6 over root 39. So work all of that out. Okay. We get root 3 over 2. Again, and a sort of a fairly nice exact answer, right? Which is root 3 over 2. Now again, that's quite a fairly nice exact form answer, right? So again, we'd be missing out on this exact answer if we were to just sub in like rounded numbers for my angles and stuff like that. So there we are. We've got these two equations here. I'm going to call them equation 3 and 4. Again, same procedure now. We want to firstly square them both to get my speed W. So doing that, we're going to get W squared sine squared theta add W squared cos squared theta to be root 3 over 2 squared add a half squared, right? And so therefore, hopefully you can see that's just going to go to W squared because sine squared and cos squared is 1, right? So then there we are. Then if I work out the right hand side, the right side simplifies to 1. So W is just also going to be 1. Okay, remember we don't do the minus with the root in here. It's just after the speed. So there we are. And so there we are, right? And again, this shows that we really should avoid trying to round and use decimals whenever we can, right? Because if we use the rounded version for beta, we'll probably get something like 0.9998 blah blah blah, right? So we would get a decimal very close to 1 but not exactly 1, so we would have missed out on this exact solution here. Okay, there we are. Then we want to find theta, so we're going to have to divide the equations. So okay, so that's going to be W sine theta over W cos theta, right? So that's going to be root 3 over 2 all divided by a half, right? So there we are. And so obviously sine over cos goes to tan, so there we are. Then if we simplify the right fraction here, so there we are. By the way, if it looks a bit awkward, you can split up the fraction like this. So root 3 over 2 physically divided by half like this, right? But there we are. We get root 3. Okay, we get root 3 there. Therefore, theta, if I do inverse tan of that, I get 60 degrees bang on. Okay, again, another nice exact answer. Okay, so there we are. And there we are. So that's my speed and that's my angle, which tells me the direction of motion. Okay, so there we are. So hopefully you're happy with that. So you can see it's basically the same process, right? But really, I guess the only added complication is you're probably going to get some sort of triangle here and you have to deal with the angles involved. But hopefully that makes sense. Okay. Then we're told in reality, the floor and the walls may not be smooth. What effect will the model have had on the speed and direction of motion you've calculated in part B? In other words, what that's basically saying is what would happen to your answer if the walls were no longer smooth and the surfaces were no longer smooth. Okay. Now remember, smooth means it has no friction. Okay. Therefore, if it was not smooth, now we're going to add friction. Okay. So what does that mean? Well, friction ultimately, right? The whole idea of friction is that it slows you down. It tries to oppose your motion, right? well, therefore the speed will slow down, it will reduce, right? So if there's friction involved, well, the speed will go down, okay? It will decrease. Okay, so that would mean my final speed of 1, which was W, right? 1, it would be less than that in reality, okay, when there would be friction. Now, what about direction of motion, or in other words, the angle, right? Well, you might think it might reduce, you might think it would change, right? Because the speed will change and stuff like that. But this is where it gets a bit interesting and a bit clever, because let me just consider and show you sort of a general collision, right? Just a general collision. So let's say I have some surface, and then it hits the surface with speed u, then it rebounds with speed v, angles alpha and beta, right? So the general thing, right? A general problem. So my general equations then, well, parallel. Okay, so if I do my components, if I just do my components here. Okay, so there we are. So hopefully happy with that. So my parallel components, right? Well, that would be v cos alpha equals u. Oh, sorry, beta. V cos beta is u cos alpha. Then perpendicular. That would be v. Oh, sorry, v sine e here. Sorry, my apologies. V sine beta perpendicular. It's going to be e lots of the original perpendicular speed, right? So it's going to be EU sine alpha. Hopefully happy with that. Now, if I was to just find the angle then, well, obviously I'll divide them, right? So if I call this equation 1 and 2, I'll divide them as usual to find the angle. So that's going to be V sine beta over V cos beta. It's going to be EU sine alpha over U cos alpha. Now, actually, when we simplify, the speeds go away. So the V's cancel, so we get tan beta, and the U's cancel, so we have E tan alpha. Okay. Now, actually, that tells me if I was to work out any of the angles, it doesn't involve the speeds at all. It only depends on E. And remember, E is just a constant, right, between 0 and 1. So the angles themselves don't depend on the speeds. So actually, yes, the speeds are decreasing, the speeds will change, but that doesn't mean the angles will change. So what we say is that the angles are independent to the speed. Okay. Independent to the speeds. Right, because you can see it in this equation here, right? Ultimately, work out any of the angles, it doesn't involve any of the speeds, right? Because tan beta is E tan alpha. Hopefully you can see that, right? That ultimately, if we can solve for the angles without involving the speeds. And so there we are. So actually wouldn't change. So the direction of motion or the angle would not change if there's friction slowing you down. And there we are. There we are. So then I've got this question here. So again, basically we're given the diagram, right? I'm not going to go over the text, right? So I've got this diagram here. Interestingly, note that now the two walls are at an angle, but doesn't really change the equations we get, really. But there we are. So then part A, okay, so work out the direction and the speed after the first collision. So if I just consider the first collision. Okay, so again, if I draw a diagram for the first part here, okay, so it's going to, again, it's going to hit the horizontal floor. It's going to hit the floor with speed 2.5, then rebound with some speed V at an angle of 45, and then some angle beta afterwards, okay? So again, if I just quickly label my components, okay? So we have 2.5 sine 45, 2.5 cos 45, then v cos beta, and then v sine beta. So then the parallel parts, okay, so that's going to be v cos beta. It's going to be 2.5 cos 45, and actually we can simplify this. If we put that in the calculator, 2.5 cos 45, we get 5 root 2 over 4. Okay, so that's my first equation. Then if I do the perpendicular, so that's going to be v sine beta. It's going to be e lots of 2.5 sine 45. And again, I can simplify this. So that means v sine beta is going to be, well, e is 0.6. So it's going to be 0.6. Lots of 2.5, lots of sine 45. So I put all that in the calculator. I get 3 root 2 over 4. Okay, that's my second equation. So now, again, solve it in the normal way. So firstly, if I solve for v, I'm going to square them. If I call this equation 1 and 2, I square them. So I'm going to get v squared sine squared beta, add v squared cos squared beta to be, it's going to be 3 root 2 over 4 squared, add 5 root 2 over 4 squared. Okay, hopefully you're with me here. So, I can, well, it will just go to v squared, right? Because sine squared over cos squared is 1. So v squared will be 17 over 4. Therefore, v, if I root this, is going to be root 17 over 2. And there we are. That's my speed there. Then I can find the angle by dividing them. So now if I do 2 divided by 1, so that's going to be v sine beta over v cos beta. It's going to be, well, 3 root 2 over 4 divided by 5 root 2 over 4. So that will go to tan beta equals, and then if I do that division, 3 root 2 over 4 divided by 5 root 2 over 4 gets me 3 over 5. So that means beta, do inverse tan of that, and that'll be 30.96 degrees. And that's my angle there. Okay, so there we are. Okay, then we need to consider the second collision. It's asking for the kinetic energy after the second collision. Okay, so obviously the second collision is going to be this part here, right, where it collides with the second surface, the second wall. So I'm going to copy that part of the diagram out, right? Okay, so that's my speed v, which we worked out to be root 17 over 2. Then it goes on to hit, then the speed after that collision I'm going to call w. And so that angle here after the second collision is theta. This is beta, remember. So this is going to be, well, if the remaining angle in the triangle has to be 180, take away 120, take away beta. So it's going to be 60, take away beta. Hopefully happy with that. Now the issue is I can't really remember. I want to consider the second wall here. Okay, now I can't split things up parallel perpendicular quite easily here. What I'm going to do instead is just consider the second wall. So I'm actually I'm just going to zoom in on this sort of diagram here. I'm going to redraw just the second wall. Okay. So there we are. So it's going to strike with speed root 17 over 2 and then rebound with speed w, as we said. The angle's theta here, and so this angle is 60 take away beta. Okay, now at this point we are just going to have to work with beta here. There's not really a way to nicely get expressions for 60 take away beta like we did before. So I'm going to just work out 60 take away beta. Okay, so 60 take away beta is going to be 60 take away 30.96, so that's going to be 29.04 degrees. Okay, so this angle is going to be 29.04 degrees. Okay, so I'm going to be using that here. And so there we are. Now we can split things up quite nicely. So it's going to go down like this, and then across like this, then up here. So this is going to be root 17 over 2 cos 29.04, and this is going to be root 17 over 2 sine 29.04. Hang on, let me write that a bit clearer. So root 17 over 2 sine 29.04, and so this is going to be w cos theta and w sine theta here. So hopefully happy with this now. Okay, so I'm just using the numerical answer for the angle because it won't be pretty if we try and simplify 60 take away beta. Okay, anyway, so now I'm going to do the same stuff, so parallel. So that's going to be w cos theta. It's going to be root 17 over 2 cos of 29.04. And there we are. We can simplify this. Okay, if we put this in the calculator, obviously we're probably going to get a decimal at this point, but there's nothing we can do about that. We're going to get 1.802 blah blah blah. Okay, and then perpendicular. We're going to get w sine theta to be root 7. It's going to be e lots of root 17 over 2 sine of 29.04. Okay. And so remember E I think was 0.6. So if we put all that in the calculator, that we're going to get w sine theta to be uh, 0.6, and then there's a bunch of zeros pretty much. So there we are. So those are my two equations. If we call this equation 3 and 4. Okay, now if you look at the question, it only wants the kinetic energy. Now remember, kinetic energy is to do with speed, so it's not asking for the angle here. So actually we just need to find the speed. So if we just square it then to get the speed, So square the two equations. We're going to get w squared sine squared theta add w squared cos squared theta to be this 0.6 squared, which is in my calculator, by the way. So I've got the whole answer on my calculator stored, and then that's going to be 1.802 blah 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 squared. Again, that's stored. So if I that means that's going to be w squared. If I square those two numbers, I get 3.609 blah blah blah. Okay, so that means if I root that, then so that's w squared. W is going to be 1.8997 blah blah blah. Okay, and that's my value for w. Then I can work out the kinetic energy. So if this is the speed after the second collision, I can work out the kinetic energy after the second collision. So Ke after second collision, well, that's going to be half mv squared. Well, in this case, the mass we're told is 0.1. Okay. And then v squared, well, it's just w, right? So it's going to be 1.8997 blah 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 squared. So we get the answer of 0.18, and then it's like 0.45, but it's just 0.18 joules to 2 decimal places there, and that is my answer. Okay. Then we got this question here. So here we're told two cushions of a snooker table, W1 and W2 meet at right angles. A snooker ball travels across the table, collides with W1 and then W2. The cushions are modelled as smooth just before the first impact. The ball is moving with speed u at an angle 20 to W1. The coefficient of restitution is 1/2 and 2/5 respectively. And firstly, it wants me to find the percentage of the ball's original kinetic energy that is lost. Okay, so it's basically asking about the kinetic energies involved. Okay. Now, obviously, it's sort of setting a practical scenario here. It's talking about snooker table and cushions and stuff like that. Don't worry, you don't need to know anything about snooker or anything like that. Now, obviously, we aren't given a diagram, but the main details are we have these two surfaces, W1, W2. We have these two walls, if you will, and we're told they meet at right angles, which means one has to be horizontal and one has to be vertical like this. Okay. And so that's going to be 90 degrees there. So they're perpendicular. Hopefully happy with that. And so basically then it's going to look pretty much the same as we've seen before. So it's going to hit the first wall here. I can call it W1 and W2 if you want. Like that. So it's going to hit the first wall here with speed u originally. Okay. And I'm told the angle originally is 20. So it's going to be 20 here. Okay. Then it's going to rebound with some speed v, and then it's going to rebound again by some speed w. Okay, and there we are. I'm not going to bother adding any more angles on. I'll call this beta because that's going to be for my first collision, but I'll add on more information as I proceed in the question, right? But that's the basic scenario here, so hopefully happy with that, right? There we are. Okay, now obviously we've got two collisions, so I'm going to consider the first one first. And if you want, you can draw a separate diagram that just focuses on the first impact. So we just got the first wall here. Then obviously we've got u, and then 20 degrees here, and then v and beta here. Okay. And there we are. Then if I do my components, so here, and then across here, then back up here. So that's going to be u sine 20 and u cos 20, then v cos beta and v sine beta here. Okay, so now obviously the parallel parts are equal to the perpendicular parts. So firstly, the parallel parts, again, that's going to be v cos beta equals u cos 20. There we are. Now, again, we could potentially evaluate cos 20, but that'll just get me an awkward decimal. I'm going to leave that there, right? That's my first equation. Then perpendicular. I'm going to get v sine beta then is going to be e, lots of the original perpendicular part of u sine 20. Okay, now actually we know what E is. So with the first wall, the coefficient of restitution is a half. So actually we can say it's going to be a half u sine 20 there. Okay. Now again, you could square both sides. If I call this equation 1 and 2, I could square them both and add them, right, in the usual way. So that'll get me v squared sine squared beta, add v squared cos squared beta to be u squared cos squared 20, add a quarter u squared sine squared 20. Then I could factorize the v squared, and then we're going to get sine squared and cos squared. So v squared is going to be, then I could factor a u squared out, and it'd be cos squared 20, add a quarter sine squared 20. Now, I can't use sine squared and cos squared equal to 1 because I've got different coefficients for cos and sine. I've got 1 cos 20, then a quarter sine 20 here. So I actually can't simplify this any further. So at that point, if I want to find v, I am going to have to just evaluate the angles and get it in decimals, right? So if I evaluate cos squared 20 and a quarter sine squared 20, I'm going to get 0.9122 blah blah blah. So if I root this, then v is going to be u lots of the root of this 0.9112 blah blah blah, right? So that's going to be 0.955. Okay, therefore v is going to be 0.955 u. So let's say 3 decimal places there. Okay, so there we are. Then I can find my angle. So now I can divide the two equations. Okay. And so that's going to get me v sine beta over v cos beta. Now that's going to be a half u sine 20 over u cos 20, right? Hopefully happy that I'm just dividing the second equation by the first one there. Hopefully happy with what I've got here. So this simplifies to tan beta. And that would be well, that's going to be a half tan 20. And if you wanted to, then you could then just evaluate beta, right? So that'd be arctan of a half tan 20, right? And so you should, you'll get the angle beta to be 10.31 to 2 decimal places, right? But there we are. So that's my speed and angle there. Now again, now I've got my second collision to deal with. So if I draw out the second part, right, where it collides with the vertical wall here, it's going to look like this, right? So it's going to strike the second wall with speed v and then rebound with speed w. Okay, there we are. As for angles, well, okay, now again, if I look at my diagram I've got here, okay, let's look at the diagram here. If I look at the triangle, this angle here has to be 90 take away beta, right? Hopefully you're happy with that, right? So this angle it approaches with is 90 take away beta. But hang on, if we was to then resolve, right? So if I was to resolve, if I extend this, right? well, hang on, I don't need to use this angle because this angle's beta, right? Because again, it's a right angle. So I can resolve based off this same angle beta here. So I can avoid the nasty angle, 90 take away beta. I can just use the angle beta instead to get the components, V cos beta and then V sine beta here. Hopefully you can see that, right? Again, and so that's a little thing we can do to avoid having to evaluate a nasty angle, 90 take away beta, right? Then here's going to be, if I call this theta then, that's going to be W cos theta and then W sine theta here. Okay, there we are. And so, my parallel parts. So that's going to be a parallel to the vertical wall is going to be these two parts here. So W cos theta is going to be V sine beta, and perpendicular. So the perpendicular to the vertical wall is now going to be the W sine theta and the V cos beta here, right? I hope you can see that. So W sine theta is going to be E, lots of V cos beta. And we know what E is, okay? We are told with the second wall, the coefficient of restitution is now 2/5, right? Pay attention to the question. The coefficient of restitutions can change because the surfaces are different, right? So here it's 2/5 for the second wall. So for the second collision, it's now 2/5 for E. So it's going to be 2/5 V cos beta there. So we've got my two equations here. Okay, hopefully happy with that. Okay, obviously again, try not to sub in beta here or V. Let's try and avoid direct substitutions and rounding as much as we can. Now, again, if I want to find W, if I call this equation 3 and 4, I can square them. So 3 squared add 4 squared is going to be W squared cos squared theta add W squared sine squared theta. It's going to be V squared sine squared beta add, well, 2/5 will go to 4/25 V squared cos squared beta. And so that'll get me just W squared. Okay, again, sine squared and cos squared will go to 1. So we just get W squared, right? If we factor that out. Anyway, we get W squared to be, then I can factor a V squared out. And then that'll be sine squared beta add 4/25 cos squared beta. Okay, again, I can't simplify this. I know it looks very convincing and enticing to try and use cos squared and sine squared, but it won't work because the coefficients are different, right? So we're just gonna have to substitute. So W squared, now V squared we do know, it was 0.955 U. Okay, I'm going to sub that in here. And that'll be squared. And then we're going to have sine squared beta. So we know that beta is 10.31. So it's going to be 10.31. And then 4/25 of cos squared of that 10.31. Okay, then at that point we're just gonna crunch it all on the calculator. Right, if we work all of that out, okay, we get W squared to be 0.170 or just 0.17 blah 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 U squared. So therefore W, if we root that answer, I'm going to get 0.413 U to 3 decimal places. And that's my speed W there. And then I can find the angle theta then, if I divide the two equations I've got. Okay, again, the same sort of procedure. So if I divide these now, that's going to be W sine theta over W cos theta. So that's going to be 2/5 V cos beta over V sine beta. Okay. And so, again, we're going to get tan theta on the left. Now, we're going to get 2/5, and then we're going to get cos over sine of beta. Okay. Now, hopefully you recognise that's actually going to be the reciprocal tan, right? If we were to flip this, we would get tan. So it's going to be 1 over tan, right? So hopefully you can see that, right? Because we got cos over sine, which is the opposite to sine over cos, so we need to flip the tan. You might recognise that's cot, right, if you've seen it already, but there we are, so hopefully happy with that. But hang on a minute, we can simplify this, because don't we know what tan beta is, right? We know what beta is, but actually we also know what tan beta is. It's here. It's a half tan 20, right? So I can sub that result in, okay, quite nicely. So it was a half tan 20, right? So therefore tan theta, if I now evaluate this in the calculator, right? So 2/5 of 1 over 0.5 tan 20, I'm going to get 2.197 blah blah blah. Therefore, if we do inverse tan of that, I get 65.5 degrees, okay, to one decimal place. And there we are. That is my angle there. So I've worked everything out, right? So hopefully happy with that, right? Now, the question is asking me for the percentage of the ball's original kinetic energy that's lost in the collisions. So lost, okay, so how much is lost overall after all the collisions are done? So it's basically asking about loss in kinetic energy. Now remember, the key formula for loss in energy with collisions is that the loss in kinetic energy is always the kinetic energy before, take away the kinetic energy after. Okay. Now, obviously, now in this case, the kinetic energy before is the initial kinetic energy. So that's going to be the kinetic energy at the start. And at the start, right, if I look at this diagram here, the starting speed is u, right? So it's going to be half mv squared. Well, it's going to be half mu squared, sorry, right? It's going to be half mu squared. We're not given a mass here, so I'm just going to call the mass m. So the initial kinetic energy is a half mu squared. Hopefully happy with that. Then what about the kinetic energy after? Well, after is after all the collisions, after the second collision. Now, what's the speed after the second collision? It's w, right? So it's going to be when the speed is w, so it's going to be a half mw squared, right? And so there we are. And actually, we know what w is. W, we saw, was 0.413 u. So I'm going to sub that in. And we're going to need to square that, right? If we square that, okay, we're going to get half m lots of. Then 0.413 squared is going to be 0.17 blah 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 u squared, okay? And there we are. So that's my kinetic energy before and after the collisions. Hopefully happy with that. Therefore, the loss in kinetic energy overall is going to be before, which is a half mu squared, take away a half m of this 0.117 u. And so then I can factor a half mu squared out, and then it's going to be 1 take away this 0.17. And so that will simplify to 0.83. Okay, I'm gonna there we are. I'm gonna round up to 2 decimal places. Okay, so that's my loss in kinetic energy. Hopefully you're with me here, right? Again, there's a lot of letters and algebra thrown around, but hopefully happy with that, right? So remember the standard formula: loss in kinetic energy is kinetic energy before the collisions, take away the kinetic energy afterwards. And so I'm just substituting my answers into here. Hopefully happy with this. So we're pretty much there now. It's asking for the percentage out of the ball's original energy that is lost. So the percentage. So it's basically asking the percentage of the energy that's lost. So if we were to do that, then we basically need to express this as a percentage. So percentage of energy lost. Well, that's going to be the kinetic energy lost over the kinetic energy initially times 100 because it's a percentage, right? Well, we can sub our answers in. So it's going to be half mu squared, lots of 0.83 for the kinetic energy loss over half mu squared initially. And that's quite nice because the half mu squareds cancel. And then if we times by 100, we get 83%. Okay, to two significant figures. Okay, and there we are. Okay, now part B is saying, in reality, the cushions may not be smooth. What effect will the model have had on the calculation on the percentage of kinetic energy remaining? So it's quite similar to one of the earlier questions we looked at. So the idea is, again, it's talking about the walls or the surfaces being smooth. So that means smooth, it means it has no friction, right? But if we remove that assumption, that means we're going to include friction. So if it's no longer smooth, we're going to account for friction. So if there's friction, well, what effect would that have on the percentage of the kinetic energy remaining, right? Now, this is important. It's talking about the percentage of kinetic energy remaining. That's not the same as the percentage we worked out just, right? This is the percentage of the kinetic energy that's lost. So the percentage of energy remaining is just going to be 17%. Okay, so hopefully you can appreciate that key difference there. This is, as we worked out, the percentage of kinetic energy lost. So remaining has to be the remaining 17%. So what that means is, if there's more friction, well, that would mean the speed would decrease, right? Because that's the whole idea. It slows you down. And so what that would therefore mean would be that there's less kinetic energy at the end. Okay? Because obviously kinetic energy depends on speed. Less speed means you have less kinetic energy. Well, therefore, less kinetic energy we have means the percentage remaining is lower, right? Therefore, percentage of kinetic energy remaining is lower. Okay. And there we are. Okay, so hopefully happy with that line of reasoning. So friction means speed will decrease, so the final speed will be lower, therefore less kinetic energy, right? And so how much kinetic energy we have left over is lower. And there we are. Now I've got this exam question here. So, okay, again, we're given all the information really on the diagram. And so part A, we need to show that the value of the coefficient restitution, E, is a quarter. So, okay, if we're going to do that, it's probably, again, best to do what we normally do. So, if I just consider the first collision, so firstly it's going to collide with that, with there, then it's going to go there, and then there. So, again, if I just draw out the first collision, it's going to look like this. So I have I have my wall here. Going to collide, and that's going to be 6 speed here at an angle alpha. Then it's going to rebound with a angle beta at speed v. Okay, so hopefully happy with this. Again, now if I split my components up, down here and across, then up here. So this is going to be 6 sine alpha, and then 6 cos alpha. Then here it's going to be v cos beta, and then v sine beta here. So if I write my parallel parts, so that's going to be, well, v cos beta, it's going to be 6 cos alpha, and then perpendicular, that's going to be v sine beta is going to be e lots of the original 6 sine alpha. Okay, and that's all I can do there. Now, I'm not told explicitly what alpha and beta are, but I am told what tan of them are. Okay. Now remember, I can exploit that to work out the expressions for sine and cos. So firstly, tan, if I'm gonna do it up here, tan alpha is 4/3. So if I do a triangle, right? So that's alpha. So again, if think about Sokotoa, the opposite side is 4 and then the adjacent is 3. If I do Pythagoras, you should get 5 there. Okay. So 3 squared and 4 squared is 25. Then you root it. Okay. So that means then sine is going to be, well, that's going to be opposite 4 over hypotenuse 5. Then cos is going to be adjacent 3 over hypotenuse 5. And those are my two expressions there. I can do the same thing for tan beta then. So tan beta, we're told, is a third. Okay, a third. So again, if I do a little triangle, I'm going to get this. So this is beta. The opposite side is 1. Adjacent is 3. Now, if I do Pythagoras on this, well, 3 squared and 1 squared is 10. So it's going to be root 10 here. Okay. So then, sine beta is going to be, well, opposite is 1 over hypotenuse root 10. Then cos, well, adjacent is 3. And then we divide by root 10 for the hypotenuse there. So those are my expressions for beta. So actually now I can easily just substitute these values into these two equations here. So if we look at firstly the parallel equation, I can simplify this then. So v lots of cos beta, well, we know cos beta is 3 over root 10, so I can sub that in. That's going to be 6 lots of cos alpha. We also know that cos alpha is 3/5, right? 3/5. And so we can simplify this then. So if I divide by the fraction 3 over root 10, I just get v. If I simplify all of this, I get 6 root 10 over 5. So that's my speed v there. Okay. Then if I look at the perpendicular equation, I can then say that v, which is 6 root 10 over 5, lots of sine beta. And now sine beta is 1 over root 10. Okay. That's going to be e lots of 6 lots of sine alpha. Okay. And we also know that sine alpha is 4/5. Okay. So if we simplify this just a little bit, so if we multiply the brackets on the left, so 6 root 10 over 5 times 1 over root 10. we get 6/5 to be 24 over 5 lots of E. Therefore, if we divide by 24 over 5, we can get E to be a quarter. Okay, and there we are. We are showing that E is a quarter. Okay, great. Okay, then in part B says find the speed of the ball immediately after it hits B to C. So B to C is the second wall here. So now we need to consider the second collision. Okay. Right. So if I now draw out the second part. Okay. So I have my wall here. So it's going to go with speed V. We said that V was 6√10 over 5. And then it's going to rebound by some speed I'm going to call W, right? That's what I want to work out. So the angles, okay, well, this angle I'm going to call theta. Now this angle here, if we look at the diagram, it's going to be this angle here. So clearly you can see that's going to be 90 take away beta, right? So there we are. Well, actually, if I now was to split it in terms of components, so again, originally, if I draw my other wall here, right? Well, actually, remember that this is beta, right? So I'm going to go across and up like that. And so actually, if you write the components, I want to write the components here in terms of beta, not 90 minus beta, because it makes my life easier. So this bit's going to be 6√10 over 5 cos beta, and then 6√10 over 5 sine beta. Again, sine because it's opposite facing the angle beta. Okay. So whatever possible, I want to avoid kind of using the angle 90 minus beta. Makes things a little bit more awkward, because then I would have to use the addition formula, which I went over at the start, to simplify it down. But you should get the exact same components that I've got here. So it just cuts down on the working if I consider using beta here. So anyway, those are my components. Hopefully happy with that. Again, then straightforward, right? We're going to go across and up here. So this is W cos theta and W sine theta here. Right. Okay, so then I'm going to do the parallel and perpendicular. But remember, I'm considering the second wall here. So that means firstly the parallel parts, right? So the parallel to the vertical wall is going to be this and this part here, right? That's going along the wall. So that's going to be W cos theta. It's going to be 6√10 over 5 sine beta. Okay, and then if I do the same for the perpendicular parts, right? So that's going to be W sine theta. It's going to be E lots of the original 6√10 over 5 cos beta. Okay, and right. So I'm going to leave that there. Now, I can actually simplify these equations because, again, I know expressions for sine and cos beta. Again, I did that in part A. So remember, sine and cos beta are here. So sine's 1 over √10 and cos is 3 over √10. Okay. So this is going to be 6√10 over 5, lots of 1 over √10. And then here it's going to be E, lots of 6√10 over 5, lots of 3, no, sorry, 3 over √10 for cos beta here, right? Okay, so I could simplify this. So W cos theta is 6√10 over 5 or 1 over √10. That will go to Six over five. Okay. So W cos theta is 6/5. Okay. And here, well, actually, we're going to need E. I believe we're told E. Let me have a look at the question. We're told, yes, okay, so it's not going to be a quarter that we did in part A because it's different walls. So actually, it's now a half for the second wall. Okay, so again, pay attention to the question. So it's going to be half here for E. So we can simplify all of this, work out these fractions. So that's going to be a half times 6 root 10 over 5 times by 3 over root 10. And so we get 9/5. Okay, and there we are. Again, now I've got these two equations. I'm going to call them equation 3 and 4. Okay, now I only want the speed, if you remember. So I only want W. So to do that, I'm just going to square and add them. Okay. So that's going to be W squared sine squared theta add W squared cos squared theta. It's going to be 9/5 squared add 6/5 squared. And so therefore W squared, because remember it will go to sine squared and cos squared, which is 1 if we factor that out. If I simplify the fractions on the right, I get 117/25. Okay. Therefore, if I root that, okay, I get 3 root 13/5, and that is my speed W there. Okay, and there we are. Okay, then part C, again, you get these weird questions sometimes. It suggests 2 ways in which the model could be refined to make it more realistic. Now, that's referring to the modelling assumptions, and actually the kind of hint here about what you can say, because it says by modelling the ball as a particle, that's the first main assumption, and then the wall is smooth, that's the second one. Okay, so actually we can tackle both of those to get my two different ways. So the first way, okay, but firstly, the ball is a particle. What does that mean? Well, it means several things. It means firstly, the ball is a single point, so it's like got no dimensions pretty much. The second one being there are no rotational effects that act on the ball or the object, so it won't rotate or anything like that. So for example, say if it was like a car on a road, normally it will skid and all that, and it will rotate and turn. It won't happen here. But the main assumption, I think, what you want to use is that when things are particles, we ignore air resistance on them. So that's going to be my critique here. So to make it more realistic, we should account, or the model should account for air resistance. Okay, that's going to be probably the standard one you can use. So that's due to the ball being a particle. Now, what about the walls being smooth? Well, we discussed this earlier, I believe. So that means if the wall is smooth, there's no friction. In reality, there would be friction, right? So again, the model should account for for friction between the ball and the walls. Okay, and there we are. So those are like the two main, like the standard critiques you can use to make to criticize the model, the assumptions, and how you can make it more realistic. Okay, now we're going to be looking at multiple collisions, but now with vectors, right? And remember, again, we looked at vectors last time, so make sure you're comfortable with that before we look at this, right? But here we are. So I've got my two walls, right, and I'm told they're at right angles, so it's going to look like this, right? We've got a horizontal one and then a vertical one like that, okay? That makes sense because we're told the walls are parallel to I and J, which makes sense because this is sort of like the x-axis or I, right? And this is parallel to J, or sort of the y-axis, right? So there we are, right? Hopefully happy with that. Now, as for velocities, the initial velocity is 5i minus 4j. So if I call the initial one 5 minus 4 like this, to help me visualise that, well, 5 minus 4 is a column vector. That tells me I'm going to go 5 to the right, and then 4 down, right? And there we are. So my velocity u, there we are. It's going to strike the first wall like that, okay? Now, I'm not going to call this u. I'm just going to literally just use the column vector for it instead. So it's 5 minus 4. Okay, so I'm just going to write the velocity 5 minus 4 here. Okay, then it's going to rebound like that, okay? And the velocity afterwards, we're told, is 5i and 2j. So 5, 2 like that, okay? And then it's going to rebound something like that, right? I'm going to call that w, right? There we are. So hopefully you're happy with the situation here, okay? Now, okay, so you might be thinking, well, I want to find w. Well, I've already got my two velocities in the first collision. Do I even need to consider the first collision? Usually it's a good idea to, you might be able to work something out that you're not realising. And actually notice we're not told what the coefficient restitution is exactly. So we might be able to get that from the first collision, okay? Now, so that's what we're going to do. So let's consider the first collision, okay? Now, remember with vectors, we don't really consider the angles. I'm not going to label any angles on here. So I'm just going to split up the components. So again, it's going to go down like this, then across the floor, then back up here. And so there we are. Now, the components themselves, well, we're going down. It's going to be by minus 4. Well, it's going to go down physically by 4 units. But because it's a vector, it's negative 4 because it's going downwards in the negative direction. But physically, it's going down by 4 units. Okay, then it's going to go across by 5. Okay, and then afterwards, it's still going to go across by 5, then up by 2. And so hopefully that makes sense. Now, obviously, if I was to do my parallel and perpendicular, well, the parallel one's redundant, right? Because all that will tell me is 5 equals 5. Great, it tells me I've done it right, probably, but doesn't tell me anything. Then the perpendicular. Now, the component the 2, right, it's going to be e lots of the original component 4, okay? And well, there we are. We can work out e. E is going to be 2 over 4, which is a quarter, and so we've found e then, and so there we are. Great. Okay. Then I'm going to now consider the second collision. And I'm going to just draw out the second collision by itself. So remember, we're just colliding with the vertical wall now. It's going to approach the wall, the second wall, with this velocity 5-2. 5-2. Then rebound by some speed w. Okay. And a velocity w. And there we are. So then if I split up my components again, we're going to go across, then up, then across like that. Okay. Now, we're going to go across here by 5 because we're going to the right. So that matches the I component. Then up by 2 because that's the J component, right? Okay, I don't know what the vector W is. I'm going to call vector WAB. So we're going to go up by B, because B is the J component, so that's the vertical part, and then A across. Okay, hopefully happy with that. So now I can consider the parallel and perpendicular parts in this scenario. So the parallel parts along the wall is B and 2. So B equals 2. There we are. Then perpendicular So that's going to tell me that we have A and 5, so it's going to be A is going to be E lots of the original component 5. Okay, now also notice A is going to be negative, right, because A is going to the left in the negative direction, so we actually need to pay attention and negate that. Okay, and there we are. But there we are. So we also know E is minus a half. Okay, now to double check that, the question mentioned the coefficients of restitution are the same for both walls, so we can reuse E to be a half, which we just worked out. Okay, so just to clarify on that. Right, so we got minus a half times 5, and so A is just minus 5 over 2. And there we are. So I've got my two components. So W, which was AB, is minus 5 over 2, 2. And there we are. That is my velocity at the end there. Okay. But it's not asked for that. It asks for the kinetic energy lost. Okay. Now, again, the loss in kinetic energy, the formula we use is going to be the kinetic energy before, take away the kinetic energy after. Okay, so in this case, where the kinetic energy before, the original kinetic energy, well, that's going to be when the velocity was this 5 minus 4 here originally. So it's going to be half times m, lots of the magnitude of the vector 5 minus 4 squared, right? Yes, okay, there we are. And so let's work that out. It's going to be half m, and then it's going to be the root of 5 squared and minus 4 squared if we work out the modulus, and then that squared, right? Now, obviously, we'll just put, if we're squaring a square root, we're just going to get rid of the root. So it's going to be half m lots of 5 squared and minus 4 squared, like that. And so we work all that out. We can simplify this. We get 41 over 2m. Okay, again, we don't know what the mass is. I'm just going to call it m, right? Then we can similarly work out the kinetic energy at the end after. Well, that's going to be half m, lots of the final speed. So it's w, right? But we saw that w is minus 5 over 2 and 2. So it's going to be the modulus of that. Okay, all squared. So if we work that out, that's going to be the root of minus 5 over 2 squared, add 2 squared, right? And then that'll be rooted, and then we square again. So that'd be minus 5 over 2 squared, add 2 squared. Okay, if we just chuck all that in the calculator, we get the we get 41 over 8 lots of m, and that's my simplified answer there. Okay, so therefore the total loss in energy is going to be the kinetic energy before, which is 41 over 2m, take away 41 over 8m, and that will simplify to 123 over 8 lots of m, and there we are. So that's how much energy is lost in terms of m there. Oh, we're told the mass is just m, so we can't simplify that anymore, but there we are. And now part B is asking for the total angle for which the sphere is deflected. Okay, so it's talking about the total angle of deflection. Okay, now we have looked at angle deflection last time, but we've only looked at it for a single collision, right? The added complication here is obviously we've got multiple collisions. So how are we going to work out the total angle deflection? And we can kind of calculate it in probably the way you expect, right? I can consider them individually. Okay, so if I look at the first collision firstly, so here, to visualize the angle deflection, remember we can extend, say, the initial velocity like this. And so the angle deflection, which remember, it tells me how I change direction. Well, I'm going to go like this, right? So that's how, that's my angle deflection there. Okay, hopefully happy with that. And so let's call that angle, let's say X, right? This whole angle here. Now, we don't need to faff about by finding like alpha and beta, right? All the individual angles. Because actually, because I've got vectors, it works out quite nicely. Let me draw out just that angle here. Okay, so there we are. This is angle X. Okay, like that. And so so that velocity there is 5,2. Okay, that vector there, and this vector here would be 5 minus 4. So hopefully you're happy with that, right? That's just the diagram for the angle there. So hopefully happy with that. And actually now, how can we calculate the angle between these two vectors? Well, if you think back to Corpuscle 1, I can use this formula here, right? So cos theta is a dot b over mod a times mod b. So I can just use this formula here, okay? To work out the angle between these two velocities. Hopefully happy with this, right? So hopefully happy the angle deflection here of the first collision between these two velocity vectors. And so I'm just going to use this formula now to work out this angle here. So, okay, so that's going to be cos x. Okay, that's going to be 5,2 dotted with 5 minus 4 over the modulus of 5,2. The modulus of 5,2, which is going to be 5 squared at 2 squared, times by the modulus 5 minus 4, so 5 squared add minus 4, all squared. And so at that point, it's just a case of putting it in the calculator. So if I simplify this, well, that's going to be 5 lots of 5 add 2 lots of minus 4 over root 29 times root 41. Okay, and so at that point I can simplify to get cos x to be, if I work all this out, right, that's going to be at 0.493 blah blah blah. Okay, therefore to inverse cos I get x to be 60.46 blah blah blah. Okay, I'm not going to round it because I'm going to be using this answer again. Okay, so I'm going to leave it like that, but that is my angle deflection for the first collision there. So hopefully happy with that. Okay, so I'm going to store that in my calculator because, as I said, I'm going to reuse that. Now I'm going to do the same for this second collision here. Okay, so then if I extend this vector here like this, again you can see the angle deflection is going to go like that. And so my angle deflection here is going to be this whole angle here, which is, I'm going to call y. Okay, I'm going to call y. And so again, if I draw that out, okay, I'm going to draw it out like this. And so 5,2 is going to be the vector there. And then minus 5 over 2 and 2, the vector there. Okay, so hopefully happy with this diagram here, which matches what's going on over there. Okay, so that's the angle deflection for the second collision. And again, I can use the same formula to work out the angle deflection y here. So cos y is going to be 5,2 dotted with minus 5 over 2, 2, all over the root of 5 squared add 2 squared times by the root of minus 5 over 2 squared, add 2 squared. And so at that point, again, it's just a job for the calculator. So that will go to 5 lots of minus 5 over 2, add 2 lots of 2. And that would be all over root 29 times by the root of 41 over 4. Okay, and so that's cos y. And so if I simplify this, I get cos y to be minus 0.493, blah, blah, blah. Okay, so hopefully happy with that. And simply, I can do inverse cos lastly to get the angle to be 119.538, blah, blah, blah. So that's my second angle deflection. Okay, the angle deflection for the second collision. Now, so those are my two individual angle deflections, right, for my two individual collisions, but they want the total angle deflection. Now, what I'm saying is, I'm saying that that my direction is changing by x degrees, and then it's going to change again by y degrees. That's what the angle deflection is doing. So what I'm saying is the direction changes by 60.46 degrees, and then it changes by further 119.538 degrees. Hopefully happy with that. Therefore, we can say the total angle deflection which is going to be just x add y, right? So the two individual deflections added together. And so that's going to be this 60.46. And now you can see why I wanted to store my answer. I'm going to reuse my answers here. So if I add all these two angles together, I get 180 exactly. Okay, so there we are. That is my angle of my total angle deflection there. So that's saying overall I've changed direction, or I've turned by 180 degrees overall. Okay, and so there we are. And so yeah, so that's the strategy, by the way. If they ever ask you to work out the angle deflection across multiple collisions, you can just work out the individual deflections and then add them like this. Okay, so we've got some exam questions on this then. So here we are, the particle P is moving with velocity 4i minus j on a smooth horizontal plane. Particle collides with a smooth vertical wall and rebounds with velocity I plus 3j. The coefficient restitution between P and the wall is E. Find the value of E. Now, you hopefully you have seen my previous video, or you have seen that how you can deal with vectors when the surface is sloped, so it's not vertical or horizontal like that. Okay, and what we've seen is we can use these two formulas, which you do have to learn. Okay, they're not in any formula book. It's going to be v dot w is u dot w, and v dot I is minus EU dot I. Again, I've done many examples using this in the last video, so hopefully you are familiar with this, but there we are. Now, how do I know the wall is not, how do I know the wall's sloped here? The key giveaway is that if I look at my two velocity vectors, so initially, so u is 4 minus 1 and v is 1, 3. The key giveaway is that none of the components are the same. The I component 4 goes to 1, and the j component minus 1 goes to 3. None of the components remain the same. So that tells me it has to be sloped, okay? Because then both components will change. The other giveaway is well, 6 marks. Okay, if we was to just compare the coefficients, you wouldn't get all that for 6 marks. Anyway, so we're going to have to resort to these formulas here. Okay, now we already know what u and v are. Okay, so we're going to need I and w potentially. Well, we can work out I, can't we? Because we know u and v, so we can work out I using our standard formula mv take away mu, which you should be familiar with. So I, in this case, is going to be m. We're not told the mass, but that's actually going to be fine. Okay, so I'm going to factor the mass out. I'm going to call it m. Then v is 1/3. Take away u, which is 4 minus 1. So if I simplify this, I is going to be m lots of 1 minus 4 is minus 3. 3 plus 1 is 4, right? Double negative there. And so that's my impulse vector. But if you again remember what I said about this last time, for the vectors w and I, okay, I just care about a direction vector, okay, for w and I. So I just care about a multiple of the vector, right? So actually, if that is my true impulse vector, if I just want a direction vector, I can just take the vector minus 3, 4, because m at the end of the day is a multiple. It's just a multiple, so I can just cancel down the multiple and get that physical direction vector there. So that's what I'm going to take for I here. Okay, and there we are. Now I could work out w. Maybe I might need to in a moment, but for now I have enough information to work out e, because I can use the second formula there. Okay, so v dot I is going to be minus eu dot I. So if I sub in these 3 vectors I've got here, okay, into the equation, so hopefully you're with me here. So therefore v dot I is going to be 1/3 dotted with minus 3, 4. That's going to be minus e lots of u, which is 4 minus 1, dotted with I, which is minus 3, 4. Then we just need to work out the dot products, right? Fairly straightforward. So it's going to be 1 lots of minus 3, add up 3 lots of 4. It's going to be minus e lots of 4 lots of minus 3 minus 1 lots of 4. And so we simplify all of this. We're going to get minus 3 at 12 is going to be 9. That's going to be minus e lots of minus 16, I believe. So therefore e has to be 9/16, and that is my coefficient restitution there. So there we are. So I can just apply the standard formula which I've done, which I've looked at previously, to work out the information there. Then we're told after the collision, P goes on to hit a second smooth vertical wall which is parallel to I. Okay, now at this point, it's talking about second collision. At this point, I'm probably going to want to draw a diagram, right, and to just help me out here. Now, as for the first collision, as I discussed, it's going to be an awkward wall. It's going to be slanted. So to help me visualize that, I'm going to consider my 2 velocities here before and after the first collision. So if I note it here, okay, so let's do it down here. Remember, u was 4, 1, I believe. Yeah, 4 minus 1, sorry, 4 minus 1. So I can draw what that vector looks like, right? So that tells me I'm going to go 4 across to the right, then 1 down, right? Think back to GCSE column vectors. So my vector u will look like that. Then v, okay, now v is 1, 3. Okay, so what that's going to look like is I'm going to go 1 across, then 3 up. Okay, so my velocity vector is going to look like that afterwards. Okay, so that means before the first collision it's going to move like that, and then afterwards it's going to look like that, which means hopefully you can see then that the wall, if I draw it down here, the wall is going to look something like that. Okay, so you can see it's slanted a little bit there. Okay, so I'm going to add these vectors on. So u here, which was 4 minus 1, and then v here, 1, 3. Okay, so hopefully happy with that. Hopefully happy with how I deduced what the two vectors look like here by just drawing the vectors. And so then I could draw the wall like that. Okay. Right. Let me get rid of all this now. So let me continue with the question. So yeah, hopefully happy with that. Okay, I'm told the second vertical wall is parallel to I. Now I again is horizontal, right? It's going to be a horizontal line like that, right? Because it's like I, right, or the x-axis, right? So it's actually going to be a horizontal, right? So if the velocity afterwards is going to go like upward like that, that means it's going to hit like some sort of ceiling, right? So it's going to be a horizontal wall like that, right? So you can see it's going to approach a ceiling like that. So hopefully happy with that, right? Hopefully happy with that second wall there, okay? Because it has to be in the direction of I, which is basically like the x-axis. So it has to be some sort of ceiling as it travels up. Okay, then afterwards you can imagine it's going to bounce off like something like that, all right? So I'm going to call that W. Right, I'll call it W here. Right, so that's really it. That's all my velocities and walls. So hopefully happy with that diagram. Right, I'm told the coefficient restitution here is a third. The angle through which the direction of motion has been deflected by in the second wall is alpha. So we need to find the angle deflection with the second collision here. So the angle deflection, okay, here after the second collision, again to help me visualize that, if I extend the before velocity like that, okay, hopefully you can see the angle deflection is going to be there. So this angle is going to be my alpha. Okay, then notice how alpha is between my two vectors, right? Like this. So this is W here, and this is my 1, 3 velocity there. So I can just use my standard cosine formula, right? So again, x dot y over mod x mod y. Now, the only difficulty is I don't have the vector for W. So to find my velocity here, I'm going to have to, again, well, actually, I could just compare coefficients because it's completely horizontal wall. But I'm just going to actually just use the formulas again, okay? And so remember, that's going to be, that is v dot w is u dot w, and v dot I is minus eu dot I. Now, please don't get confused. W here is, I probably should use different letters. I'm going to call this W something different, okay? I'm going to call it, I'll call it Z, okay? I'll call it speed Z. W is the direction of the wall vector, so it's the wall, okay? So there we are. Anyway, so I'm going to use these two formulas now. So I'm going to quote that here, that here, V again is 1, 3. Okay, Z, my velocity afterwards, Z is going to be AB. Okay, I want to find A and B. Now, I can't work out what my impulse is going to be as it stands, but I can actually work out what my wall vector is going to be, my direction vector for the wall W here, right? Because again, notice I'm told the second wall is parallel to I. Well, there we are. So it's in the direction of I, which is 1, 0, right? So the wall vector has this direction vector 1, 0, because that's the direction it's going in. Hopefully happy with that, right? So in the direction of I, it's in the direction vector 1, 0, because that is I, right? That is what the vector I is, 1, 0. Right, so I can take W to be 1, 0. And actually now I can work out a direction vector for I. Now remember what I said was, because the wall is perpendicular to the impulse always, right, because the impulse is designed to be perpendicular to the surface, I can flip the vector, so it's going to go to 0, 1, then negate one of them. Okay, so I could just do 0, -1. Okay, and there we are. So I've got all my 4 ingredients now. I also know that E is a half. No, it's a third, was it? Let me have a look at the question. E. Yes, E was a third. Okay, E was a third. So I've got all my ingredients now. I can use my vector formulas here to work out Z. Sorry, Z. So if I look at my first equation, so that's going to be V dot W is U dot W. Now in this case, it's quite confusing again. So this is my initial velocity and Z is my after velocity. So it's going to be AB dotted with W equals the initial velocity 13 dotted with W. Okay, hopefully happy with that. Again, I probably could have made my variables a bit more distinct. So U and V here are just general vectors for the before and after velocities. They're not the U and V are used in part A. I just want to clarify that. But that's the general vector formula. I'm not substituting U and V in from part A. They're different vectors. Okay. And in fact, I'll make it even clearer here that U is referring here in the formula to be the velocity before, and V is referring to the velocity after. Okay, so there we are. So hopefully you're happy with that. Hopefully there's no questions. Hopefully I haven't confused you too much. Anyway, so I can work out these dot products. So it's going to be simply A is going to be 1 lots of 1, add 3 lots of 0. But the zeros go away, so I'll just get A's 1 very nicely. Okay, and there we are. Then if I look at the second formula, so now that's saying V dot I is minus EU dot I. So in this case, that's going to be AB for my velocity afterwards, dotted with I, which we said was 0 -1. It's going to be minus E, so that's going to be minus a third for E, dotted with the velocity before, which is 13, dotted with I, which is 0 -1. And so at that point, we're going to get minus B is going to be minus a third of, well, 1 times 0 is 0, so we get 3 lots of -1. Okay, therefore, minus B is going to be minus 3 lots of minus a third is going to be 1, so therefore B is -1. Okay, so hopefully happy with that. So my velocity afterwards, Z, is going to be AB, which is 1 -1. Okay, so now I'm in a position to now work out the angle deflection. So here Z, I've just worked out to be 1 -1. Okay, so therefore if I use this standard formula from Corpure, the angle alpha here, it's going to be cos alpha, it's going to be 13 dotted with 1 -1 over the modulus of 1 squared add 3 squared times by the root of 1 squared add -1 squared. So if I now simplify this fraction, that's going to go to 1 lots of 1 add 3 lots of -1 over, and if I simplify the roots, I'm going to get root 10 times by root 2. So if I simplify all of this, well, 1 minus 3 is going to go to -2 over root 20. Therefore alpha then, so that's cos alpha, right? So then if I just do inverse cos of that, okay, that will get me that therefore alpha is going to be 116.565 blah 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 degrees, right? And there we are. Now, what did the question want me to do? It wanted me to round it to the nearest whole number. Okay, so simply, if I look at my answer, round it to the nearest whole number, it's going to go to 117. Okay, and that's my and that is my answer for alpha there. Okay, so hopefully happy with that. That's the angle deflection there after the second collision. Okay, so the angle between those two velocities there. And I've got this question here. So I'm not going to read the question out here because it basically just describes what we've got in the diagram here. But I'll make a note of the key information as we go. Right, so part A is asking for the full range of possible values of E. Okay, well, obviously you're not going to get 3 marks for saying that E is between 0 and 1. We're obviously going to have to tighten this inequality somehow, okay? How are we going to do that? Well, I don't know, but again, usual advice is just do the question normally, do the same steps, do the same procedure, and then we can work from there. Okay, so again, so we've got to focus on this first collision here first, between this floor here, R to S. So let me just draw that out then, right? So this is my first collision. So we've got the floor like this. Okay, it's gonna hit the floor here with a speed. We're told the velocity before is 6 minus 8. Okay, so it's going to be 6 minus 8. Okay, and there we are. And then it's going to rebound like that. Okay, and I'm not told what that vector is. I'm just going to call it a V. Okay, so hopefully happy with that. So I'm just considering the first collision. Hopefully happy with my diagram here. Now, because the wall is completely flat here, it's completely horizontal, you could just split the components up because they will be parallel and perpendicular quite nicely here. But suppose you're a bit wary, suppose you're not sure whether you should be using the vector formulas, which v dot w is u dot w and v dot I is minus eu dot I. Suppose you're a bit wary about, oh, should I be using this? Can I use it or do I not need to? You can use these formulas for any vectors question, right? Even when you don't need to. Let's just say you're a bit wary, a bit anxious, and you're going to do this. Let me just use the formulas here, okay? So in this case, obviously we've got u to be the vector 6 minus 8. V, now I don't know what the vector V is, that's what I'm going to work out. I'm going to call it AB. And, okay, what about, I don't know what an impulse vector is going to be, but I am told the direction of the walls. I'm told that the vector RS is in the direction of I. Now, this is the wall, RS. So, if the wall vector is in the direction of I, well, I is just 1, 0. So that's going to be my wall vector, right? So my wall vector, I can say it's going to be 1, 0 there, right? Because it's parallel to I, which is 1, 0. So there we are. So I can take that wall vector there. So hopefully happy with that. And actually, therefore, I can also find the impulse from that, right? Because remember, my trick is if I can work out the wall or the impulse vector by flipping the other one. So if I flip 1, 0, that will go to 0, 1. Then I negate one of the components. So let's say I take minus 1 there. So I can find an impulse direction vector like that. And now I've got all my ingredients to use the formulas here. So firstly, v dot w is u dot w. Well, in this case, that's going to be AB for V, dotted with 1, 0 for W. Is going to be 6 minus 8 for U, dotted with 1, 0. And so that'll get me A is equal to 6. quite nicely. Okay, and there we are. And then the second one, that's going to be v dot I is minus eu dot I. And so that's going to be AB dotted with 0 minus 1 for I is going to be minus E. I'm not told what E is, so I'm just going to leave it as E. Minus E, lots of U, which is 6 minus 8, dotted with I again. And so I can simplify this expression. So I'm going to get minus B to be minus E lots of plus 8. Okay. And there we are. So minus B is minus 8E. So B is 8E. And there we are. Okay. So I've got my two components for V. So V is AB, as I discussed, which is just 6, 8E there. Okay. And as I said, because the wall was completely flat, you could just compare coefficients as well with the vector, but you can always use the vector formulas to be safe. Okay, so that's the method there. So that's all I can really deduce, right? So I've worked out my velocity vector. It's the only thing I can do, right? So I can only use the two equations. How from that am I going to get? How on earth from that am I going to deduce what E can be? Okay. Right. Okay, this is where it's a bit tricky to realise. It might have stumped a few students. So this is my velocity vector. So I'm going to write it up here. So V is 6, 8E. Okay, so that's my velocity vector then. So I can say it's going to be 6, 8E. Okay, and so that's my velocity vector there. Now I can't do anything else. I can't pluck any more equations out of thin air. So that's all I've got to work with, really. Okay. So the question is asking for the range of possible values of E. So how am I going to get from this velocity vector to kind of work out what E can be? Well, obviously the velocity vector is in terms of E, right? So let's see what happens as we change E, right? So obviously E, as I discussed, is between 0 and 1. So let's see what happens when E is 0. So if E is 0, V is going to be 6, 0. And then when E is 1, V is going to be 6, 8. Okay. So those are sort of like the range of values for the vector, right? So the vector V can, the velocity can be between 6, 0 and 6, 8. Okay, effectively. So how can I use that? Well, the only other information I'm given in the question is that the other wall vector, the other wall ST has the vector 2, 2i and j. So the wall vector here is going to be 2, 1. Okay, so that's going to be the direction of the wall. Well, one thing I'm noticing here is, as I just discussed, my velocity vector is between 6, 0 and 6, 8. It's kind of staring at me that if I triple it, it will be in sort of the, if I triple this, right? Okay. I'm going to get the vector 6, 3. And so this vector here, 6, 3, is sort of in between 6, 0 and 6, 8, right? Hopefully you can see that. So maybe it might be helpful to kind of equate the vector 6, 8E and see what E can be when it equals this. So 6, 3, let's say is equal to the velocity, okay? So it's going to be 6, 8E. Therefore, we can deduce 8E has to be 3. So E is going to be 3 over 8, okay? And so when E is equal to 3 over 8, well, the velocity here is going to be 6, 3. And that's going to match the direction of the wall, which is also 6, 3. Well, hang on, the two vectors are equal, so they have the same direction vector. So these direction vectors are equal. So that tells me that in this case, the velocity V is going to match the wall like that, okay, with the same vectors. So the same direction, they're parallel, as you can see here. But that's an issue because you can see, obviously, they're not parallel because they're going to meet these two sort of lines and vectors here. So that actually tells me what I need to do to this value of E. So this value of E is where they start to be parallel, but I want them to intersect. So I'm going to need to sort of make V less steep. So it's sort of like that, and then they do cross, okay? So in order to do that, well, the vector has to be sort of smaller, right? So E has to be reduced. And so there we are. So I'm going to say, in order for V to meet the wall, and then if I get rid of this, E has to be less than 3/8, okay? Because when it's equal to 3/8, that's when the vector and the wall have the same vector, so they're parallel, okay? So they're parallel like that, but I don't want them to be parallel. I want V to be less steep, so I need to reduce the vector down, okay? And so I get this inequality here, and there we are. And now it says to find the full range of values. So remember, we need to combine with the general inequality from 0 to 1. So it could be between 0 and 3/8 there, okay? But actually, this is where if this question isn't bad enough, that's where they try and trick you there as well, because it's actually just going to be strictly above 0. It's going to be strictly greater than 0, because remember, E is the perpendicular component, as we can see. So remember, the velocity vector was 6 and 8E. As we can see here, if E is 0, it will go to 6, 0. So that means it's just going to sort of be horizontal like that. And it's still not really going to rebound off, because the wall is inclined at an angle. We do need there to be some sort of verticality to this velocity. So there needs to be some sort of trajectory, and it goes up off the ground in order to hit the wall at an angle. So we do need there to be a vertical component to the we do need there to be a vertical component for the velocity. So E has to be above 0 to make sure there's a J component going up, because then that will hit the wall like that. That's vertical, okay? So yeah, very, very sneaky, and there we are, okay? Very, very tricky that is. And I must say, I believe the mark scheme, you get 2 marks for just finding the velocity vector, which is just standard procedure, right? So just used the 2 equations, right, to work out the velocity vector in the normal way. You only get 1 mark for then deducing the range of values of E. So actually, if you were a bit stuck about how to find the values of E, that's literally only 1 mark, okay? And actually, you don't need that for part B, because we're told E is 1/4, and actually part B is going to be fairly standard as well. So you can still get 9 out of 10 marks if you're a bit stuck about this whole stuff here with the E. And so that's why don't be put off by the questions. Still try to do as much as you can, because you'll pick up more marks than you think, okay? Sometimes the mark scheme's a bit more generous than you think. Anyway, so that's the question there. Okay, then we're told it's now given that E is 1/4 and the coefficient restitution is 1/2 with the second wall. And so we need to find, in terms of I and J, the velocity after the impact with the second wall. Okay, so I'm going to get rid of all this now, right? So now it's asking about the second collision. So it just wants me to find the velocity. Okay, it's fairly standard now. I'm given all the values. Okay, so it's just a standard procedure at this point. So I'm just going to draw out the second collision. Okay, so we've got the wall that's slanted like this. And so it's going to income with the, it's going to be incoming with the vector V, which we worked out to be 6, 8E. And then it's going to rebound by some velocity W. And so hopefully happy that. That's my second wall, ST. That's my second collision. Okay, so we just need to find W here. So hopefully happy with that again. Again, if you're a bit confused by the end of the with the end of the first part, you can put that to one side. It's literally just, again, just working out the speed after a collision in the normal way. And actually, I know what E is. Okay, so E, we're told, is a quarter. So actually, I can simplify V. So if E is a quarter, V is going to be 6 and then 8 lots of a quarter, which is going to be 6, 2. So I can simplify that quite nicely. And there we are. I also know that my wall vector, as I just discussed previously, the wall vector is 6 minus... No, sorry. It's going to be 2, I and J. That's with the second wall. So it's going to be 2, 1. So that's going to be my wall vector. Okay, 2, 1. Okay. So W is 2, 1. So that's the direction for the wall vector. Hope you're happy with that. Hopefully happy with that. V again is 6, 2. W, I don't know what W is. I'm going to call that, actually I'm going to call that Z, okay, not to confuse you with W for the wall vector. I'm going to call it Z, okay. So the final velocity Z, I'm going to call CD, okay. And then I can also work out an impulse vector, because again, if my wall vector is 2, 1, then because the impulse is perpendicular, I can flip it to 1, 2, then I negate one of them. So let's say I do minus 1, 2 there. And so at that point, okay, if I get rid of this, at that point, I'm going to use the standard vector formulas, right? So that's going to be V dot W is U dot W, and V dot I is minus EU dot I. Okay, so there we are. So if I use the first equation, now V, now in the formula, V is the final velocity, so it's going to be Z. So Z dot W is going to be U dot W, but again, U is the initial velocity, so it's going to be V. So V dot W there. And then so we can simplify that. We can substitute our stuff in. So Z is CD dotted with W, which is 2, 1, equals V, which is 6, 2 dotted with 2, 1. Okay, and then I can simplify that. So it's going to be 2C add D. It's going to be 6 lots of 2 add 2 lots of 1. And so we get 2C add D. That's going to be 14. When we simplify, so hopefully happy with that. Then if I use the second equation, that's going to be V dot I is minus EU dot I, but again that's going to be Z dot I is going to be minus EV dot I. Okay, so that's going to be, if I substitute my vectors in, that's going to be CD for Z dotted with, what was it, minus 1, 2 for I. Yep. Okay. That's going to be minus E. Now E, for the second collision, it's a half. Okay. So remember, pay attention to the question. The coefficients of restitution can be different between different walls. So now it's a half, okay? So it's going to be minus a half, lots of V, which was 6, 2, dotted with I, which is minus 1, 2. Okay, then I can simplify this. So I'm going to get minus C at 2D. It's going to be minus a half, lots of minus 6 add 4. So that's going to be minus C plus 2D to be minus a. If I can work this all out, I can work it all in one go. So minus a half times minus 2. That's going to be plus 1, and there we are. That's my second equation there. And so at that point, again, I've got simultaneous equations. So I have 2C plus D was 14. And also we've got minus C plus 2D is 1. So I'm going to solve these equations simultaneously. Again, it's just G to C now. Now to do that, I can double the second equation to get minus 2C add 4D is 2. If I rewrite the first equation, hopefully you can see I can now add these equations to get rid of the C. So 5D becomes 16. Therefore D is 16 over 5. Then I can work out C by substituting that in. So I'm going to sub D into, let's say 2C of D is 14 in the top equation here. Okay. Now, if I do that, I'm going to get that 2c add 16 over 5 for d is going to be 14. Okay, therefore, 2c on its own is going to be 54 over 5. Therefore, c is going to be, divide that by 2, I get 27 over 5. And there we are. So my velocity overall, again, z is cd, which here is going to be 27 over 5 and 16 over 5. And there we are. That's my answer there. Okay, so again, I'm hopefully happy with that, and hopefully happy with how we use these vector formulas there. Again, I went over that with many examples in the previous part, so hopefully you are comfortable with that. But there we are. There we are. So again, hopefully you can see that wasn't too bad, especially compared to part A. That was hopefully you're happy with that. So really, again, you could realistically get 9 out of 10 marks really for just doing like the standard methods of using the vector formulas to work out the missing velocities, right? And so there we are. Okay, so we're in the final part of this video here, and now we're going to be looking at some trickier problems that have a bit more trickier trigonometry and algebra to them. Now, before we actually jump into the questions, I want to look at two particular common techniques that you will see crop up in the various questions here. Okay, now I want to go over them in more detail here before we look at the questions, because hopefully then you have a rough idea about these, and you have them in the back of your mind. Because the questions they don't really go over this in detail; they just jump from one thing to another without explaining the stuff in between, right? And you'll find as well you're going to need to have these in the back of your mind, or else it'd be actually quite hard to do those part of the questions. So let's go over them now, right? So we got this first scenario here. So we are given these two addition formulas for sine and cos. Now that these two identities you will see from year 2 pure for normal maths if you haven't already. So hopefully you have seen them, but there they are if you haven't. And again, that is in the formula book. Okay, they're not written as nicely as that, but they're in the formula book there. Okay, so you don't need to memorize them really, but there we are. Right, so these formulas exist. Right, and so the first part wants me to say to use these formulas to find a simplified expression for sine of 90 minus theta and cos of 90 minus theta, right? So we're just going to apply these formulas. So sine of 90 minus theta firstly. Well, I'm going to be using the sine formula here, right? Now you can clearly see if I want 90 to take away theta, I'm going to have to take A to be 90 and B to be theta, right? Hopefully you can see that. So if I sub that in, I'm going to get sine 90 cos theta, take away cos 90 sine theta. Now what we can do to simplify, well, we can evaluate sine and cos 90. Now sine 90 will go to 1 and cos 90 will go to 0. So it will just go to cos theta, take away 0, or we just get cos theta on its own. And there we are. So sine of 90 take away theta quite nicely just goes to cos. Okay. We can also do the same sort of thing for cos. Okay, so cos of 90 take away theta. Now we're going to use then the cos formula here. And again, A is going to be 90, B is theta. So if we do cos 90 minus theta using the formula, hopefully you see that will go to cos 90 cos theta, take away sine 90 sine theta. And again, cos 90 will go to 0 and sine 90 will go to 1. Oh no, sorry, plus wasn't it? It's a plus. My apologies. Right, so therefore it will just simplify to sine theta. Okay. And there we are. So again, they simplify surprisingly nicely, right? Quite interestingly. And there we are. So hopefully happy with that, right? Now, the second part says, hence show that tan of 90 minus theta is cot theta. Now, what you also need to know, if you don't already, if you haven't seen it from pure year 2, normal maths, you need to remember that cot theta is the same as just 1 over tan. Okay, so there we are. Okay, now it wants me to show that tan 90 minus theta goes to that. Tan 90 minus theta, but we have sine and cos of 90 take away theta. Well, hang on then, how are we going to get tan? Hopefully you're thinking we can use the identity that tan is sine over cos, right? And so then at that point, we can now substitute our results that we just looked at. So sine of 90 take away theta goes to cos, and cos of 90 take away theta goes to sine. Well then, hang on, isn't this just the reciprocal tan? Because tan is sine over cos. We flip it, so we get 1 over tan. Okay, and that is cot. Okay. And so there we are. We have shown that tan 90 minus theta is cot. Okay. Now, you might be thinking, well, can't I just directly use the formula for tan here from the formula book, right? To evaluate tan of 90 minus theta directly. If you was to do that, okay, if you was to evaluate tan 90 minus theta using this formula, that would be tan 90 minus tan theta over 1 plus tan 90 tan theta. But the issue is, hopefully you can see, we're going to need to evaluate tan 90, which is undefined. So we can't directly use the tan formula, so we're going to need to split it to sine over cos and do it that way. But that would still be perfectly defined, right? This would only this will be defined as long as theta isn't 0, because then 90 take away 0 is 90 and tan 90 is undefined. But usually theta won't be 0 anyway, so formulas are fine. Okay, anyway, so I just want to go over that, right? So hopefully you're happy that ultimately tan 90 minus theta goes to cot there. Right, and then the final part says, further show that if tan x is equal to cot y, then x is 90 degrees take away y. Okay, so I'm going to write that down here, right? So we have tan x is equal to cot y. Now the aim is we want to show that x is 90 take away y. Okay, so how are we going to get that, right? Now hopefully you can see that we're going to need to use the identity we just proved, right? So we know that cot theta is tan of 90 minus theta. Well, we have cot y, so we can say that cot y is going to be 90. Is going to be tan of 90 take away y, right? Hopefully happy with that. I'm just using the identity we proved previously. Therefore, tan x, if we sub that result in, is going to be tan of 90 minus y. And now, well, you can probably see we can just directly compare and equate the angles. And so we can do just that. So x is 90, take away y there. Now, obviously, you are right to be very cautious about just jumping to equating the angles, right? Now, technically, we wouldn't be able to do this because technically, if we was to compare tan of two angles, we'd be saying x is 90 take away y. And then, obviously, tan repeats every 180 degrees. So it's going to be then multiples of 180. So it's going to be 180k, right? But k is just a multiple, right? But the thing is, what we're also told is that both angles x and y are between 0 and 90. Okay. So what that would mean is, well, if y is between 0 and 90, well, actually, 90 take away y is also between 0 and 90. Right? Because if y was 90, then 90 take away 90 is 0. And then if y is 0, then 90 take away 0 is 90. So it's, again, between 0 and 90. So if this value is between 0 and 90, and x is between 0 and 90, well, we cannot possibly add on or take away 180, because that would exceed the range 0 to 90. So that forces k to be 0. So we cannot add or take away 180. And that is, again, because x and y are between 0 and 90. Okay? And so, because they're both between 0 and 90, we can just basically say the angles are the same in that particular case. Okay, we can just equate the angles because we don't need to consider any multiples of 180. And so that is the explanation there. But what you will find with questions and mark schemes that we're going to look at, and literally just jump from, they literally do this step in one jump. They don't even bother justifying it. They just equate the angles like that. So I just want to break it down now so you're convinced and you're happy with this sort of technique here. Okay, so we are going to be looking at this sort of thing where if we got tan of two angles, we can equate the angles. Right, and this is the other common technique that you need to be aware of. Okay, so we have this diagram here, which is just a standard sort of multiple collision situation, right? And so in the first part, it wants me to write down the angle deflection for the first and the second collisions in terms of alpha and beta. Okay, so remember the angle deflection, we have looked at this before. Now the angle deflection, if I was to look at the first collision, right, if I was to extend the initial sort of velocity, right, like that, well, it turns out this angle would be alpha because they're going to be vertically opposite. Okay, so that's going to be alpha. And so the angle deflection then is going to be this whole angle here, right? The angle deflection tells is the direction of turn. Okay, and so you can see that the angle deflection here is going to be alpha beta. Okay, and that's usually pretty much always the case. You just add the two angles. Okay, so the angle deflection there is going to be alpha beta. Okay, so that's for my first collision. Now for the second collision then, again, if I was to extend the initial or the before speed like that, and again this angle then, okay, it's not going to be 90 minus alpha. Okay, that was in an awkward spot. Okay, well this angle is going to be 90 minus alpha. But what about this angle here? Well, that's also going to be the angle before, which is 90 take away beta. Okay. And so again, the angle deflection then is going to be this whole. It's going to be that whole angle here. And so the angle deflection here then, well, it's going to be these two angles added together, right? So it's going to be 90 at alpha and then the 90 at beta here. Okay, so 90 take away alpha, sorry, and then 90 take away beta, and that goes 180 take away alpha, take away beta. Okay, so that's the angle deflection for the second collision there. Okay, so those are my two angle deflections. Then it says in the second part, hence show that the total angle deflection is 180. So to find the total angle deflection, I kind of alluded to this in one of the previous questions. The total angle deflection, when you got multiple collisions, we just add all the individual angle deflections together. So therefore the total angle deflection it's going to be these two added together, right? So it's going to be alpha and beta for the first one. And then the 180, take away alpha, take away beta for the second one. And so we simplify this. Well, the alpha and betas cancel, so we just get 180. And there we are. Okay. There we are. And then it says in the lastly, hence further show that the velocities v and u are moving parallel to each other, and that the object is moving opposite to the original direction. Okay, so what does this mean then? If the total angle deflection is 180 degrees, so the total angle deflection is telling me, well, how much in total the angle of change direction by after the collisions. So if I've turned 180 degrees from before to after, so let's say before, okay, so this was my before velocity u. So before I was travelling like this, right? Now if I am now turning by 180 degrees, you can then see I'm going to be on the same line but backwards like that. That's a 180 degree turn. So I've sort of rotated, I've sort of flipped direction. And so that is what this means. So the total angle deflection is 180. I've turned by 180 degrees overall across the collisions. Therefore, that results in the direction being parallel and opposite. Okay. So I'm going to say very briefly that the object has in total turned 180 degrees to the original direction or velocity, right? And therefore therefore it's moving opposite to the original direction. Because again, it's going to be that sort of situation like this diagram there. Okay, and therefore that would also mean the velocities are parallel, right? Because if this was a u and then that's a v afterwards, it's the same sort of direction, it's just in opposite directions. Okay, but there we are. So that's it. So again, hopefully happy with that, right? So again, like with questions, they basically they don't give any explanation. So I've decided to split up the process here, right? So in essence, if you want to show anything about the direction of something or the path of something, or if you want to show the velocities are parallel, the main idea is you want to consider the total angle deflection. So you want to calculate the angle deflection for both the collisions, and hopefully you should get it 180 degrees. In that case, then it has to then be flipped in the opposite direction, so it would be moving opposite. Okay. But there we are. So I thought I'd go over that explicitly now before we look at some questions. Okay, so we've got this question here. So we've told two vertical walls meet at right angles at the corner of a room. A small smooth sphere slides across a floor and bounces off each wall in turn. Just before the first impact, the sphere is moving with speed u at an acute angle alpha to the wall. Coefficient restitution between the wall and the sphere is e. Find the speed of direction after the second collision. Right, so again, let's draw the situation first. So we've got two vertical walls at right angles. So they're going to look like this. So one's horizontal and one's going to be vertical like that. So there we are. Okay, then I'm told a small smooth sphere slides across the floor and bounces off each wall in turn. Okay, now I want to clarify, you might think, this is where the question's a bit deceptive. It says that the sphere slides across the floor. You might be thinking it's just on the floor moving forward like this. The thing is, if I was to draw this as a big rectangle, basically the whole situation is on the floor. But that doesn't mean it's on this sort of wall. It just means it will still move in the same way, where it will initially bump into the floor like this. And so we're told the speed is u initially, and the angle's alpha. So I just want to clarify that. So yeah. So this is the situation we're dealing with, but this whole thing is basically on some sort of big floor overall. That's what it means by sliding across the floor. It's referring to this whole like rectangular box, right? It's a bit confusing, right? But I want to clarify. It's a standard collision, right? Right, so get that out of the right. So let's move on. So we're told that's really it, and we're also told the coefficient restitution is e. So really, they're being really vague with us, and they're just really generalised the problem, right? So we've got initial speed u, initial angle alpha. Okay, let's just proceed. So again, it's going to rebound with some speed v and an angle beta. Okay. So again, we're going to do the same situation. So if I split up the components first, this is going to be u sine alpha, and then u cos alpha here, then v cos beta, and then v sine beta here. Hopefully happy with that. So again, I'm going to do my two equations. So the parallel parts. So v cos beta has to equal u cos alpha. There we are. That's my first equation. I also, if I then now do the perpendicular components. So that's going to be v sine beta. That's going to be e lots of the original u sine alpha. Okay, so eu sine alpha. And there we are. Those are my two equations, right? Okay, now, again, what I would normally do is I'd square both the equations, right? So if I call this equation 1 and 2, I'd square them, then add them to get the speed v. But if I was to do that, I can't work out the speed here, at least nicely. If I was to square them like that, I'd essentially get that v squared is going to be u squared cos squared alpha. Actually, I'll factor it out. It's going to be u squared lots of cos squared alpha and e squared sine squared alpha. Okay, that's what you'd eventually get to if you was to square then add them, right? But I can't simplify this bit because again the coefficients are different. Okay, it's not cos squared and sine squared, it's cos squared and e squared sine squared. So this will not go to 1, so I can't simplify that. So I can't find really a nice expression for v. So I'm just going to leave that there, okay? So the only other thing I can do is divide them to get the angle. So now if I divide them, okay? So it's going to be v sine beta over v cos beta. That's going to be eu sine alpha over u cos alpha. Hopefully happy with that. And then again, that'll go to tan beta is E tan alpha. And there we are. Okay. So again, I can't do anything more with that. So that's really it. So if I now do the second collision, okay, so it's going to rebound like that with some other speed W. So this angle here is going to be 90 take away beta. Okay, and then this angle here is going to be, let's say, theta, right? So hopefully happy with that. Now I'm going to draw out the second collision, right? I'm going to draw that out separately, not to confuse. So if I draw out the second collision, so it's the vertical wall now, and so it's going to collide with speed v and rebound with speed w. And this is the angle theta, and as we discussed, this is 90 take away beta, okay? However, remember, if I was to do the first wall like this, remember I should be avoiding using 90 take away beta, because this angle is going to be beta, right? So I can say that this component is v cos beta, and here is v sine beta. So I am avoiding using the more complicated angle because I'm just going to stick with beta. Okay, so hopefully happy with that. So these are my components before. Then if I resolve here, we're going to go across then up like that. So this is going to be W cos theta and W sine theta, like that. Hopefully happy with that, right? Hopefully happy with that. So again, if I do my parallel and perpendicular components, so parallel, well, parallel to the vertical wall here, you can see that W cos theta will equal V sine beta. Then if I then do the perpendicular equation, so perpendicular to the wall, well, that's going to be this W sine theta and V cos beta. So W sine theta then, and that's going to be E lots of the original V cos beta. Okay, so hopefully happy with that. And so those are my standard equations there, my parallel and perpendicular equations. Hopefully happy so far. Now again, I could square them and add them to get my speed W, but again, like with the first collision, okay, when we did that with the first collision, we're gonna have E involved, so we won't be able to nicely simplify and find the speed. So I'm not gonna bother. Okay, so all I'm gonna do is divide the equations instead. Okay, so if I divide the equations like this, so W sine theta over W cos theta, that's going to be EV cos beta over V sine beta. Okay, and so that will get me tan theta to be well, the V's will cancel, so you're going to get E lots of cos over sine beta. Okay, and actually, what do you notice? Well, this is just tan flipped, right? Because remember, tan is sine over cos, right? So cos over sine is the reciprocal, so therefore tan theta is going to be E over tan theta, right? Tan beta, right? Hopefully happy with that, right? So again, I've just done a little bit of trig there, right? So hopefully happy with how I've got to this point. Now, it's not terribly clear how I can simplify this any further, but then think back to what we did previously. From the first collision, we deduced that tan beta is E tan alpha. So let's substitute that in, okay? So therefore tan theta is going to be E over E tan alpha. So therefore tan theta is just 1 over tan alpha. Okay, and there we are. Now, this is the really difficult point in the question, right? How can we proceed from here? So we sort of got an equation, right? We sort of want to solve this equation, right? We kind of want to find theta and alpha. Now, we've got tan theta and tan alpha, but obviously the issue is I have 1 over tan alpha, so I can't just equate the tans, right? So I'm going to need to somehow simplify this fraction here. Well, what we could say is that 1 over tan alpha, again, tan is sine over cos. So if I flip it, this is cos over sine alpha, okay? So I could have a bit of a brainwave here and think back to the very first diagram here. So sine alpha and cos alpha come from these components here, right? Now, very similar to what I discussed with the second collision, right? Remember, technically the angle for the second collision is 90 take away beta, but we use beta instead. What if we kind of did the reverse, right? So if I go back to the first diagram, so instead of using alpha here then, what if we then considered this angle here? And so this is a right angle, so this angle here is going to be 90 minus alpha. Now I'm going to just draw this out bigger so I'll make it clearer, okay? So Okay, so this angle is 90 minus alpha. This angle's alpha, okay? Obviously, this is the initial speed u. So I'm just copying out sort of the triangle here, right? And so we said this is u cos alpha, and this side is u sine alpha, right? Now, what if instead, okay, what if we, instead of considering alpha here, what if we did SOHCAHTOA to the angle 90 minus alpha? Now, you might realise, due to SOHCAHTOA, you might realise the sine and the coses will flip to the opposite. Now, you might realise from here that because we sort of flip the angles, instead of alpha, now we're considering the other angle here, that the sort of things will flip. So the sine will turn to cos and the cos will turn to sine. But anyway, let me just consider then doing SOHCAHTOA to 90 minus alpha. Now, the 90 minus alpha angle is opposite this side here. So this was u cos alpha, but alternatively, we could say this is u sine of 90 minus alpha, right? Likewise, for this side here, it's adjacent to the angle. So we could alternatively say u sine alpha is u cos of 90 minus alpha, right? And so we've got sort of equivalent representations for the two sides. Now, tan alpha then, right, which is the expression we want to consider, right? Tan alpha, well, it's going to be u sine alpha over u cos alpha, right, due to SOHCAHTOA. But actually, we know but equivalently, we know that u sine alpha is u cos of 90 minus alpha. Same for u cos alpha. We now can see it's equivalent to u sine of 90 minus alpha. Again, there we are. And so we can see then that this goes to cos over sine of 90 minus alpha. So it's going to be the reciprocal of tan of 90 minus alpha. Hopefully you can see that, right? Hopefully you can see, because we have cos over sine, that's the reciprocal tan, so it flips tan. So we get 1 over tan 90 minus alpha. So there we are. So we deduce, so if I write this down here, we deduce this sort of identity here, right? That tan alpha is flipped to 1 over tan 90 minus alpha, which is what we want, right? Because we have 1 over tan. So if I substitute this result, okay, if I substitute this result where we got up to, right? So tan alpha is so 1 over tan alpha. Now tan alpha, as we discussed, was 1 over tan of 90 minus alpha. Well, hang on, doesn't that just then simplify the tan of 90 minus alpha, right? Because we've got 1 over this, then we could just flip it like that. And so tan alpha is now just tan of 90 minus alpha. And now we can very nicely sort of solve this equation with theta and alpha, right? Because now they're both just simply tans. So we can compare, okay? So that's one way you can do it. That's one way you can deduce this, sort of the more intuitive way, where, because so we got up to this point, right? But I couldn't solve for theta and alpha because the tans were sort of different. So I then I considered cos over sine, and I sort of found an alternative expression for cos over sine alpha, because if you remember, we got sine and cos alpha from the first collision like this. So I just looked at my diagram to consider the other angle, 90 minus alpha, then it did SOHCAHTOA to that, and it worked out quite nicely. Now that's the more sort of the longer but the sort of more slightly more intuitive way to get that result, okay? The other way you could do this is, if you think back to the common techniques we did, right? One of the common techniques we said was that cot theta was tan of 90 minus theta. So the more direct way you could get to, if you get from this result to that to this from tan theta to 1 over tan alpha to then tan theta is tan 90 minus alpha, you could just directly use that identity there. But I imagine you probably don't want to learn extra identities and stuff like that. You can learn this identity if you want to. This is one of the common techniques we use, but obviously you'd be a bit stumped if you didn't know that identity, right? And that's understandable. It's quite it's not an identity we see very often. So that's the direct way. But if you didn't remember the identity, you probably have to do that sort of idea instead, where we can split tan up to sine over cos or cos over sine. Then you sort of need to find another way of expressing that, right? By looking at your triangles. And then you can deduce this identity at the end, okay? Right, again, very nasty part of the question there. Hopefully you're somewhat with me here. Now again, thinking back to my common techniques, when we got this situation here with tan or two angles, because the two angles are going to be less than 90, okay, we're told that in the question, right? The angle alpha is acute, okay? And very quickly, theta is also less than 90 because this angle here, 90 minus beta, is less than 90 because this angle is 90 degrees. It's a right angle triangle, meaning the remaining angles in the triangle are forced to be less than 90. So this is less than 90. So the angle after the collision, theta, is also less than 90 because in any given collision, the angle is reduced very quickly. That is because for any general collision, tan beta, you'll deduce that tan beta is E lots of the original angle tan alpha. Now, E is less than or equal to 1, right? So that means tan beta would be less than or equal to tan alpha. Therefore, beta is less than or equal to alpha. So the angle afterwards is reduced. So theta has to be less than 90 if the original angle here is also less than 90. So essentially, alpha and theta are both less than 90, which means because we have tan of theta is tan of 90 minus alpha, we can equate them. Okay, so theta is 90 minus alpha. Okay, and again, we can equate them because both theta and alpha are less than 90. Okay, but usually they don't expect any justification. They just jump to this step automatically. But yeah, remember that's one of the common techniques we looked at. If you have tan or two angles, the common technique we can do usually is then we can just equate the angles. So there we are. So that's my final angle theta. Now, it's asking for the speed and direction of motion. Okay, now direction of motion. Now usually the direction of motion is the angle, but they're looking to be a bit more specific here. Okay, and this is where if you remember, we're going to use the other common technique. Okay, they're looking for something a bit more specific. Now, because theta is 90 minus alpha, what we're going to do then, if it's asking for direction of motion, what we can do is consider the angle deflections, right? We cannot, if we want to work out direction of motion, we can just work out the angle deflections. Okay, it's the same thing, right? So we can work out the angle deflections for the two collisions. So this collision, firstly, the first collision, the angle deflection is just the two angles added together. So alpha and beta here added together, right? Again, we looked at that previously. I'm not going to go over that in too much depth here. So for the first collision, angle deflection is alpha and beta. Okay. And then we can do the same for the second collision. Okay. So the angle deflection there, well, if I look at my diagram for the second collision, well, the two angles now, before and after, are 90 take away beta and theta. So it's going to be 90 take away theta, no, 90 take away beta, add theta. Right, so again, I'll just add the before and after angles. Now we can simplify this because we know what beta is. It's 90 take away alpha. So it's 90 take away beta, add 90 take away alpha. And so that would be 180 take away alpha, take away beta. So what we can then do is consider the total angle deflection. And remember, that's one of the common techniques. If you want to work out the direction of motion or the path of something, consider the total angle deflection. And so in this case, it simplifies quite nicely. So it's going to be the two angles deflections added together, right, to get my total. So it's going to be alpha beta from the first one, and then 180 take away alpha, take away beta from the second. And hopefully you can see it just goes to 180 because the alpha and betas cancel. And that's quite a significant result, because remember, again, we looked at this in the common techniques. When it's 180 degrees for the total angle deflection, that's telling me overall I've turned by 180 degrees. So if my initial direction or my initial velocity looked like that, then at the end, if I rotate by 180 degrees, then I'm going to be on the same sort of line, but in the other direction. I've reversed, right? So that's what they're looking for. So the direction of motion afterwards is reversed to the original direction, or opposite to the original direction. Or we could say the original velocity. Okay, either way, the idea is that we at the end we move opposite to where we're moving at the start. Okay, and so we can deduce that because the angle deflection totally is 180 degrees, so we turned overall by 180 to get the opposite direction. Again, very sneaky, quite hard to see that, but again, it's one of the common techniques, right? So if you have that in the back of your mind, then you think, oh, if I want to work out any direction of motion, consider the angle deflection, then it might tell me what it might look like. Okay, now what about the speed w, right? Now, if I go back to my equations, so these are my standard parallel and perpendicular equations for w, right? Now, again, as I discussed, the usual technique is we'll square the equations, right? Add them, and then we can get w squared, and then find w that way. Again, as I discussed, we won't be able to find w nicely by squaring the equations because we have e involved, so it's not gonna solve very nicely. It's going to look like this, right? So we did this with the first equation and it looks horrible. We've got cos squared and sine squareds everywhere, right? And then it's just nasty. We won't be able to find w that way. Now, what we do have, of course, is theta, right? We have theta is 90 minus alpha. So what I'm thinking is we can go a bit more back to basics and just substitute theta in and find w that way, right? Rather than squaring them. Now, if I now obviously, what equation do I pick then to substitute theta into? Well, I can't use the perpendicular one because it has an e in. That's not going to help. I want to avoid the e if I can. So I'm going to pick the parallel one. So w cos theta again is v sine beta. But we also know that theta is 90 minus alpha. So if I sub that in, that's again v sine beta. Now we can actually simplify this. It looks ugly, right? We have cos of 90 minus alpha, but that is we can sort of expand that in the usual way of using the addition or the compound formula, right? Which again you hopefully would have seen from normal maths, but we're given the formula for it here, right? Now we want cos of 90 minus alpha. We can essentially expand it and simplify it by using the formula. Hopefully you're happy to see that this will simplify too. If we use the formula, that will go to cos 90 cos alpha plus sine 90 sine alpha. And then, well, cos 90 goes to 0 and sine 90 goes to 1. Therefore, this all will just simplify to sine alpha. So actually, cos 90 minus alpha is sine alpha. Okay, if we sort of simplify that. So therefore, w sine alpha is v sine beta. Now, where on earth can we go from here? Well, let's have a look at my first collision and my first set of equations. Okay. Here, right? So these are my two equations initially. Well, hang on a minute. Look at this. I have an expression for v sine beta here. V sine beta is EU sine alpha. So I can substitute that in right here. So W sine alpha is V sine beta, which is also EU sine alpha. And this works quite nicely because then we can cancel the sine alphas. So W is just EU. And that is actually the expression for W there, which is what they want, okay? Right, so we've got this exam question here then. And, okay, we're giving all the information on the diagram, right? So firstly, for 7 marks, we need to show that 10⁵ alpha is a third. Okay, seems really random. How am I going to do that? Not quite sure, but I'm just going to do the standard procedure, right? So I'm going to consider the collisions and then find the parallel and the perpendicular equations. So if I consider the first collision, first of all, so that's going to be here, right? So we approach this floor here. So it approaches with speed v at an angle alpha. Then it's going to rebound with some speed, I'm going to say w, right? And at an angle beta, let's say, right? And so at that point, I'm going to do my components. So we're going to go down here and across here, then across here, then back up here. Hopefully happy with that. So this is going to be v cos alpha, and then sorry, v sine alpha, and then v cos, right? So again, this is sine because it's opposite the angle, and then this bit's going to be v cos. Then this is going to be w cos beta and w sine beta here. And so then if I do my parallel parts, so it's going to be here. So that's w cos beta is v cos alpha. And then as for the perpendicular parts here and here, if I do my perpendicular equation, so that's going to be w sine beta is going to be e lots of the original v sine alpha. Now we know what the coefficient restitution is. With the first wall, which is a to b, it's 2/3. Okay, so we can sub in 2/3 for e here, and there we are. So those are my two equations. Okay. Again, so if I call this equation 1 and 2, again, you might be tempted to square them and add them. If you do that, okay, if we do that, you're going to arrive at w squared is going to be v squared lots of cos squared alpha. Then 2/3 squared will be 4/9, so it'd be plus 4/9 sine squared alpha. So you can see again, we're not going to be able to deduce we won't be able to deduce what w is because I can't simplify this trig expression because it's not cos squared and sine squared, it's cos squared and 4/9 lots of sine squared. So I can't do anything else to this. So the only other thing I can do is divide them, right? So that's going to tell me that w sine beta over w cos beta is 2/3 v sine alpha over v cos alpha, and then you can see that tan beta is going to be 2/3 lots of tan alpha. Okay, and there we are. It's the only thing I can deduce there. Okay, so then let's consider the next collision. So this is going to be w here. As I said, this angle here is beta. Okay, so then we're going to approach. We're going to approach with this angle here. Now, what this angle is also going to be beta in this instance up here, right? Because notice I've got two parallel lines, so I'm going to need to think back to G to C. And remember, I've got a Z shape, right? So I've got two parallel lines like this. And I've got a Z shape like that. So if this angle's beta, this angle's also beta because they're alternate angles. They make a Z shape, right? Like that. Okay, so we've got a Z. We've got Z angles. We've got alternate angles, so they're equal. Again, that's from G to C. Okay, so hopefully you're happy with that. So this angle here, as it approaches the second collision, is also beta because they're alternate. Okay, so that's the first thing to pay attention to here. That could trip you up, but there we are. So then, if I do my second collision. So it's going to approach the vertical wall like this. Okay, so it's going to approach here with speed W with an angle beta, which we just discussed. Then rebound by a speed Z. Are we told the angle? Yes, we know the angle is a half alpha. Okay, so there we are. So there we are. Hopefully happy with that. So really, again, it's just, I know it's a bit of algebra. There's a lot of letters, but hopefully you recognise it's the same process. Again, I'm just doing the parallel and the perpendicular equations, simplifying by dividing the equations, which we normally do. The only complication, again, is to recognise that we get beta here because we got alternate angles. But anyway, we're going to do the exact same process here. So if I now split my components up, so we're going to go up here, then across, and then across, and then down like that. And so this is going to be W sine beta, W cos beta here, then Z cos of a half alpha, and then Z sine of a half alpha there. So hopefully happy with these components here. So then the parallel equations. So parallel to the wall here is going to be Z cos of a half alpha is going to be W cos beta. And then if I do my perpendicular equation with the perpendicular components here, okay, that's going to tell me that Z sine of a half alpha is going to be E lots of W sine beta. Now we know what E is here, the coefficient restitution. We're told the second wall is also 2/3. Okay, so I'm going to sub 2/3 in here. And there we are. So hopefully happy with that. These are my two equations. And so again, you might be thinking, well, usually we square the equations, right? So if we call this equation 3 and 4, we'd square them, then add them. But we're not going to get Z nicely because the sine and the coses have different coefficients. So we have W cos and then 2/3 W sine. So the only thing, the best thing to do is divide. Okay, so divide like usual. So if we divide the two equations, we are going to get Z sine of a half alpha over Z cos of a half alpha. And that's going to be 2/3 W sine beta over W cos beta. And then that will reduce to tan of a half alpha is going to be 2/3 tan beta. And there we are. Now that's not what they're looking for exactly, but we're quite close. We got tan of a half alpha. We need to show it equals a third. Okay, well, we've got tan of half alpha equal to 2/3 tan beta. So we need to get rid of tan beta, don't we? But if I look at the first collision, we deduced that tan beta is 2/3 tan alpha. So actually, therefore, I can say that tan of a half alpha is 2/3 of 2/3 tan alpha. Okay, therefore tan of a half alpha is going to be 4/9 tan alpha. Okay, now hopefully you can kind of see how we would continue to solve this, right? Because hopefully you can see it resembles a double angle, right? So we have a half alpha on the left, and an alpha on the right. Okay. So the next thing I can do is set up a double angle. Now, to make that really clear, I can say I can let x to be a half alpha, right? So then that would be tan x is 4/9 tan 2x. And so you can clearly see it's a double angle, and so I can use my trig identities, which are in the formula book, right? Now I'm not given what I'm not given what tan of 2 theta is going to be. I'm not given the double angle formula, but I can work it out using this formula given to me in the formula book. So tan of 2 theta, okay, which is tan theta add theta. So we're gonna set both a and b to be theta in the equation. So it's going to be tan theta add tan theta over 1 minus tan theta, and that will simplify to 2 tan theta over 1 minus tan squared theta. And so there we are. So tan 2 theta is 2 tan theta over 1 minus tan squared. That's how you can do that with the formula book. So I can sub that in. So I'm going to say, and tan 2x is also going to be 2 tan x over 1 minus tan squared x. Yep. So if I substitute that in then into this equation here, therefore tan x is going to be 4/9. Actually, I'm going to rearrange this. Tan x, so if I divide by 4/9, I'm going to get 9/4 tan x is tan 2x, okay? Then I can clearly substitute that in. So 9/4 tan x is going to be 2 tan x over 1 minus tan squared. Then I can multiply across by 1 minus tan squared. And that would be 2 tan x. I shouldn't expand here. I don't need to, because I can just factor a tan x then to all the terms. So then that would be 9/4, lots of 1 minus tan squared x. Take away 2 equals 0. Hopefully happy with how I've got that here. So just factor in a tan x out of every term like that. Then I can expand inside the bracket to make it a bit nicer. So I have 9/4 minus 9/4 tan squared x minus 2 equal to 0. Then I can say that tan x is equal to 0, or 9/4 tan squared x. If I set this whole bracket equal to 0, you can see that 9/4 tan squared is going to be 9/4, take away 2. And so at that point, if I now simplify this equation here, I'm going to get 9/4 tan squared x is going to be 9/4 take away 2 is going to be 1/4. So if I then divide by 9/4, I get tan squared x to be 1/9. Okay, and so therefore, if I root both sides, I get tan x to be plus or minus root 1/9. Okay, so that would be tan x is positive 1/3 or negative 1/3. And there we are. And so actually, if I now bring all these equations together. So we need to solve tan x is 0, or tan x is equal to 1/3, or tan x is minus 1/3. And so we need to go on to solve all of them, right? And so then if I solve all these three individually, okay, this part first, inverse tan of 0 gets me x is 0. Then if I solve this one, inverse tan of 1/3 gets me x to be 18.434, blah, blah, blah. Or then if I solve this equation, I'm going to get x is minus 18.434. Okay. But obviously then there'd be more solutions if we add or take away 180, but I only need one solution really, okay? Let me now just consider what x can be, because usually there's a range of values for the angle, right? I am told in the question that alpha is between 0 and pi over 2, okay? Or in decimal form, that's between 0 and 90, right? But that's alpha. So if alpha's between 0 and 90, remember we said x is a half alpha, okay? So if alpha's between 0 and 90, then for x, I'm going to need to halve it, right? So x is between 0 and 45, okay? So there we are. So we only look for values for x between 0 and 45. So you can clearly see it's only going to be this one, right? So 43 to 2 decimal places. Okay, then if I find out, and then I need to find alpha, right? So remember x is a half alpha. So half alpha is 18.43. Therefore, alpha is going to be, if I double that, it's going to be 36.87 degrees. And there we are, okay? So we found alpha, but actually, the question wanted me to show that tan of a half alpha is a third. So actually, we kind of jumped the gun a little bit. We've already solved for alpha. That's not hard to do. We can show tan of a half alpha is a third. If I look at my questions then, oh, well here, we said that tan x was a third, right? So tan x must be a third, right? That's the only equation that can be true, because as we discussed, that equation has no solutions here, nor does that one. So we can only have tan theta as a third, okay? So tan theta is a third only. Well, actually, x is a half alpha. So therefore, we can say that tan of a half alpha is indeed a third, okay? And that is my answer to part A. So again, very weird question, but hopefully hopefully happy with the first part we did, where we just did the parallel and the perpendicular equations, but then we needed to use double angle formulas. Hopefully spotted and happy with the fact we're dealing with a double angle formula, and then we're just solving a trig equation that came from that. Okay, so again, really the steps are sort of nothing too unusual, because you should be able to solve trig equations. You should be able to find double angle formulas from normal maths, and also write the parallel and perpendicular equations like we normally do. But there we are. Okay, so then it says in part B to find the percentage of the initial kinetic energy that is lost after the two impacts. So again, that's now referring to the loss in kinetic energy, right? So we know how to calculate that. The standard formula for loss in kinetic energy with collisions is the kinetic energy before, take away the kinetic energy after. And so in this case, the kinetic energy before okay, well, what's the initial kinetic energy? Well, the initial speed is v, okay? So it's going to be half mv squared, okay? I'm not given a mass, I'm just going to call the mass m. So it's going to be half mv squared. Hopefully happy with that. Then the kinetic energy after, now that's referring to the kinetic energy after the second or the final collision, right? So it's going to be half m, and what's the final speed? It's w, right? Oh no, z, we called it z, didn't we? So the final speed after the second collision is z, so it's going to be z squared, okay? And there we are. And so therefore the loss in kinetic energy, if we take them away, is going to be a half mv squared take away half mz squared. And actually we can factor half m out, right? So it's going to be then v squared take away z squared. I could further factorise this because it's the difference of two squares, but I'm going to leave that there, right? Because if you remember, when we if you remember the parallel and the perpendicular equations, we can square them and then we can get the speed squared. So actually the squares of my speeds might be more helpful, so I'm going to leave it where it is, but that's my expression. So then if I go back to the question, it's asking for the percentage of the initial kinetic energy that is lost. So it's asking about the percentage loss in energy. Okay, so to work that out, so the percentage loss in kinetic energy, well, that's going to be out of the total energy we have, which was the kinetic energy initially. How much is lost? So the loss in kinetic energy out of the total kinetic energy before, and then times 100 to get it in the percentage, right? So if I substitute my expressions in here, that's going to be a half m of v squared take away z squared divided by half mv squared times 100, right? Now I can cancel the half m's out, and so that's going to be v squared take away z squared over v squared times 100. Right, now they are going to want a numerical answer, like an actual percentage. So we are going to somehow need to simplify this here. So we're going to need to find a way to deal with the v's and z's here, right? So my speed's v and z. So we essentially want to solve for v or z, right? Now, how do we usually do that, right? Well, if it was to solve for the speed, if I look back to my, let's say, these parallel perpendicular equations, what we'd usually do is we'd square them and add them, right? But if we was to do it, say here, okay, very quickly you'd get z squared to be w squared lots of cos squared beta, and then 4 over 9 sine squared. Now this won't simplify, that won't simplify any further, right? Because I can't use cos squared and sine squared as 1 here because they have different coefficients. So I'm just stuck with this expression here, and we could solve the question using this, right? If we look at other equations, but it's going to be very fiddly. Let's try and make things easier for ourselves, and actually, if we kind of take a step back and think a bit more basic, right? Well, let's just literally look at the equations. So if I look at the parallel equation, I have that I have here that z cos of a half alpha is w cos beta, right? But hang on, if we look at the first set of equations, we also have w cos beta is v cos alpha. So I can use the parallel equations, combine them, and that gets me z in terms of v quite nicely, right? So w cos beta is v cos alpha then, hopefully you can see that. Well, then I can say that v cos alpha is also z cos of half alpha. And so I've got a link, an equation with z and v. Just like that, okay? So it's a lot quicker and simpler to just look at the equations like that. I don't need to square it if I don't have to, okay? So hopefully with me here. So if I just jot it here, then let's say I have z cos of half alpha, which was w cos beta, which was also v cos alpha, right? Hopefully happy with that. So I'm just combining the equations from the the parallel equations for the two collisions, so I get an equation with z and v quite nicely there, okay? So I don't need to square it if I have to, right? I can get a nicer equation that's easy to deal with. Now obviously I've got z in terms of v, but I'm going to need to find cos alpha and cos of a half alpha, right? To simplify this equation. How am I going to do that? Well, if I look back at the question, right? So what did they ask me to do? Firstly, they wanted to be sure that tan of a half alpha is a third. Again, I've done that for a reason, right? So if tan of a half alpha is a third, Well, you might be familiar with, for example, from other chapters, we can use angles. If we have tan of an angle, we can find sine and cos, can't we? Okay, so we can do a little triangle, right? If we have tan of something, we can then find sine and cos. So I'm going to note this result here. So tan of a half alpha is a third, right? Let's use it down here. So tan of a half alpha is a third. I'm going to do it down here. So, again, we're going to do the sort of, it should be a familiar technique by now, where if we have tan of something, we can find sine and cos. So, to do that, I'm going to do a triangle. This is a half alpha, my angle. Now, if I remember SOHCAHTOA, so the 1 has to be the opposite, because, okay, tan is opposite over adjacent. So, 1 must be the opposite side and 3 is the adjacent. Now, due to Pythagoras, the hypotenuse here, well, it's going to be 3 squared and 1 squared, which is 10. So, it's going to be root 10. Hopefully happy with this, right? So, then sine of a half alpha, right? Well, that's going to be opposite over hypotenuse. So, it's going to be 1 over root 10. Likewise for cos then, well, that's adjacent over hypotenuse due to SOHCAHTOA. So it's going to be 3 over root 10. And then we are. So we've got expressions for sine and cos of a half alpha. So we have something for cos of a half alpha, don't we? It's 3 over root 10. So that's the first bit. But what about cos of alpha? Now, you might start at that point to think, well, maybe I'll do some double angles, some funny stuff, to try and obtain cos alpha from this. But actually, we don't really need to think too deeply, because if I also look back at the equations I've looked at, we have here. We have tan of a half alpha is 4 over 9 tan alpha. But hang on, isn't tan alpha a third? Tan of a half alpha a third? So if tan of a half alpha is a third, that means 4 over 9 tan alpha is a third. So just tan alpha, if I rearrange this, if I divide by 4 over 9, tan alpha is just 3 over 4. And then again, we can do the same sort of trick with the triangles to find sine and cos alpha from this. So now we have tan alpha is 3 over 4. Okay, because again, I know that tan of a half alpha is a third. So I'm just using that equation here to find the expression for tan. Anyway, tan alpha is 3 over 4. So now we're going to do the exact same technique to find sine and cos, right? So we have tan alpha was 3 over 4. So if I do the same sort of triangle, so we have angle alpha. So again, the opposite then, the opposite has to be 3 and the adjacent is 4. So Pythagoras tells me it's going to be 5 for the hypotenuse, right? Hopefully you're with me here. And so then sine of alpha, well, that's going to be opposite, which is 3 over hypotenuse 5, and cos alpha is going to be 4 over 5. And there we are. So now we also have an expression for cos alpha, which is 4 over 5. And there we are. So this is 4 over 5. And now you can kind of see that we're going to get z in terms of v quite nicely, because we know what the coses are now. So we're going to have 3 over root 10 lots of z is going to be 4/5 v. So if I want to solve for z, I'm going to divide by 3 over root 10, right? So if I do that, I get z to be 4 root 10 over 15 v. Okay, and there we are. So I'll be able to use that in my percentage here, right? Here, but of course it wants z squared, right? So I'm just going to need to square it. Okay, so if z is equal to that, then z squared, if I square that, I get 32 over 45v, and there we are, v squared, sorry, and there we are. Great. So hopefully happy with that. So at that point now, it's just a little bit of algebra and a bit of simplification. So z squared is 32 over 45z v squared. So we can simplify this to v squared, take away 32 over 45 v squared for z squared over v squared times 100. And actually, hopefully you can spot that this will all simplify now, but the v squareds will all cancel. So we're going to get 1 take away 32 over 45 over 1 times 100. And so if you just work all of that out quite simply, you get 260 over 9%, because again it's a percentage, we times by 100, or as a decimal that will go to 28.89% to 2 decimal places. And there we are, that is my percentage there. But there we are, I hope you're happy with that, but that's it. I'll see you next time.